Yeah. Hi, Parangama. No, sis. Okay. Maybe just wait for.
You want
Ah, I,
record?
I'll take it. Yeah, thank.
This machine
He's walking. This one is walking. Okay, okay,
this
okay.
have this
Yeah.
power.
Okay. Okay. Maybe just wait for 5 minutes. Yes. Just ask the organizers maybe. Denny, should we start? Should we start?
Yeah.
Hello. Hi, Parongama, can you hear me? Hello.
Yes, I can hear you. Hello, good morning.
Hi, this is Sanjeev. Yes, yeah. Okay, so it's total 40 minutes. So you'll have, let's say, 35 minutes talk and 5 minutes for the question. Is it okay?
Okay, fine. Yeah.
Okay.
Shall I keep the video on?
Yeah, I guess yes. Yes. Yeah. And is it possible to increase the volume? Because
Yeah.
you are doing it, right? Okay. So we'll just start in a minute. Okay.
Okay.
Okay, welcome everybody. So in this morning session, we have two online talks before the coffee session. So first talk is by Parongama Sen from Department of Physics, Calcutta University. And she's going to talk about extreme switches in a three-state kinetic exchange model of opinion dynamics. Yeah. So Parongama, please go ahead. It's yours.
Thank you. Let me make it full screen. Yeah. Is it visible now, full screen?
It is visible.
Hello?
Huh?
Hello?
Yeah, is the full screen visible? No.
Well, without his scan.
Okay. I think this is what probably.
Can you please check?
Yes.
I'm moving the slide. Is it moving?
It is moving. It is moving, but just maybe this. Full screen. Is it possible? But then you don't see the speaker.
Here, but I
think it's better to also have the speaker, right? Huh? Okay. Yeah.
So shall I start?
Yeah. Please go ahead. Yes.
Yeah, thank you. So very good morning to all of you, and it's really a pleasure to be here, and I must thank the organizers for giving me the opportunity to speak. Actually, I would.
Is it possible to increase the volume a bit, Parangama?
I think I have increased the volume, but I'll speak louder. Okay.
Okay. Is it
It's
possible to
better
increase
now?
the volume from here?
Just a moment. Okay. Let me see.
Okay. Can you just speak a bit?
Hello. Is it better now? Is it better? Okay, I think I have made it full now.
Okay. Can you just try it again?
Hello, can you hear me?
Now it's low, right? Just a minute.
Because I can hear you very well.
Yeah. Here it is very low. The voices. I think they're trying to do something.
Okay. So shall I wait?
That's the maximum here. Okay. So you did something earlier, no? That was, I think, is a bit better.
No, I just increased the volume in my laptop.
Just increase the volume then maybe.
No, I did that already. It's maximum.
Okay.
All I can do is I can try to speak louder. That's all.
Yeah. Maybe a bit closer to the microphone, maybe.
Yeah, that I'm trying to do that. Okay.
Yes. Okay.
So let me thank the organizers. I would have been very happy if I managed to go there and be present physically, but unfortunately that is not possible. So I think this not so good option, but okay. Still, I can share my thoughts with you. So this work which I'm going to present today is done with Kathakuli Biswas, who is actually teaching in a college, and simultaneously she is pursuing her PhD in Calcutta University. So I'll begin with a short introduction to general social phenomena and kinetic exchange models before going to the model which I'm going to talk about. So we know that there are many unconventional questions regarding social behavior, and physicists are now trying to answer these questions And these occur in various fields like how people take decisions, why do birds flock, why some people are very rich, how do diseases spread, and then other biological phenomena, etc. And the interest in these type of phenomena grew because the observation was that there are some universal laws and emergent behavior. And it was thought that there must be some hidden laws governing human beings and animals as well. So I'll just give you some examples. There are some features which was noted for the election data in various countries. You can see that these are from different European countries. Hello? Sorry?
Yeah, it's okay. Yes.
Yeah, okay. From different European countries, if you plot the scale data against a normalized number of votes, then we see that the data essentially fall one upon each other. And this figure is for wealth distribution from different countries, and also they follow the famous Pareto law, that is a power law tail. Although the exponent is a bit different, but the general behavior is similar. So when we model social behavior, there are certain assumptions which we do. One is that the society can be looked upon as a complex system, like say molecules of a gas, and the individuals behave as particles, and interactions lead to emergent features, just like in physical systems. Of course, human beings differ from, animals also differ from just molecules and atoms because they have free will. But then we assume that it's a very large system. For a sufficiently large system, those can be regarded as fluctuations, and there can be some collective or emergent behavior. And that can be described by the laws of statistical physics. Of course, there cannot be a unique model describing these things, but there are several attempts to do such, to explain such phenomena. So let us straight away come to the topic of opinion formation in a society. So this problem is actually extensively studied by physicists and from for quite some time now. Basically, you regard the opinion formation as an evolving process in which there can be some debates and arguments initially between people. Typically, there can be a situation where there are two opinions, yes and no, whether you support something or you don't. And initially, you may have different opinions. It can be a completely disordered system, so to say. But then, after the interactions, some kind of result emerges. So this is what we have in mind. And by the word consensus, we mean that all or majority of the members agree to the whatever issue is there. So one of the oldest model was a voter model, nothing to do with votes actually. In this case, in this model, what happens is that if there are, for the binary case, which is the most studied one, you have two opinions, say A and B, and there an agent just picks up a random neighbor and adopts her opinion. So people do not have any conviction in their own opinion, and this is just a copying phenomena, and this can somewhat explain how things go viral and so on. So we'll need some features of this voter model. So that's why I have introduced this model in the beginning. And if there are a fraction of agents with opinion A, then it can be easily shown that in any dimension there is a conservation that's for the ensemble averaged fraction dFA dt is equal to 0, which means FA remains constant. Of course, there are various other models, and if you are interested, there is one book which we wrote, co-authored a few years back, and there are several other models which have been discussed. So, in the title, you have seen the words kinetic exchange model occurs, and what are these kind of model? Here, you assume that just like in kinetic phenomena, there are two gas molecules coming and interacting with each other and exchanging energy. Here, we assume that there are two agents and they exchange opinions, and it's like a scattering process. So, at time t, they meet, and there are some interactions taking place, and they emerge with a different opinion, which I have written as OI and OJ. And essentially, OIT plus 1 can be, in general, a nonlinear function of OIT and OJT. And this kind of model actually was previously considered for modeling wealth distribution, in which there was a conservation that the total wealth was fixed. Here you don't have any concept of total opinion being fixed, so there's no such conservation. Okay, so if you go through a short review, then the first model in this, not the first model actually, but one of the first models which was proposed is a one parameter model in which you have this OIT and OJT. They depend on their own opinion and the opinion of the other interacting agent with some coefficient. There's only one parameter lambda, and epsilon 1 and epsilon 2 are random variables. And in this case, it was seen that below a certain lambda c, all opinion states are 0. And in this case, the opinions were taken to be continuous variables. And above lambda c, opinions either are all positive or all negative. So after this, another model was introduced in which there were two parameters. Now, the parameter with which the interaction takes place is a different one. It's called mu. It can be interpreted as an interaction parameter. And lambda is interpreted as a conviction parameter. Of course, if lambda is equal to 0, it becomes something like a voter model. And here a symmetry broken phase was found for lambda greater than a certain value. And these are all mean field results. But these models were not sufficient in the sense that if you start with two opinions which are both positive, then always after the interaction, the opinions will remain positive. In general, we take the opinions to be from -1 to +1. So then we thought that there should be some kind of a negative interaction introduced so that even after two agents with positive opinions, they interact, a negative opinion can emerge out of it. The exact mechanism and why should it be justified, etc., I'm not going into those details. Those are some social things, and there are instances where those kind of things can happen. So in this particular model, which I'm going to discuss today and its extension, we had this similar kind of equation. And although it looks like a linear equation, it is not exactly so, because there is a bound. This OI, OJ, etc., they cannot exceed +1 or cannot be less than -1. And therefore, it is actually a nonlinear model. And here, this mu ij, which is the interaction parameter, we impose that with probability p, it can become negative. Now, the mean field results show that there is actually a critical value of PC. Above PC, it is like a paramagnetic system. That means that the average opinion is 0. And below that, you have a consensus type of thing happening. Interestingly, the exponents were found to be identical to the Ising mean field exponents. And later on, it was also studied in other dimensions. Now, henceforth in this talk, we'll take mu to be equal to ±1, and the opinion values having three values, having three states ±1 and 0. This doesn't actually make the thing anything different, because the results are basically same. The PC can be a little bit different and so on. For the mean field case, it is the same PC, that is 0.25. Okay. Now, this three opinion model can be regarded as a scenario like this, where you have a left, central, right scenario, or you have a case when there are two major candidates and there are some people who abstain from casting their vote, or there are some neutral people, they haven't made up their mind, etc. Now, incidentally, this model is now popularly known as the BCHS model after the initials of the three proposers. And lots of work has been done on it. And I'm not going through them in detail, although I have a slide where those things are written down. I will just tell you that if you are interested, you can go through this recent review in Frontiers of Physics. And this one particularly focuses on the BCHS model. And on kinetic exchange models, there was one issue in philosophical transactions in 2022, I think, which also covers other social phenomena like wealth distribution, etc. So let me now go into the details of this model. So as I told you, this mu parameter is chosen to be equal to ±1. And remember, this is our governing equation for the interaction. And here we have just shown schematically how an opinion can change. So if there is the ith agent has opinion +1 and interacts with this agent who has opinion 1. Then finally, this opinion, if mu is +1, it will be 1. In other cases, it can be 1 or 0. Similarly, 0 can go to ±1 as well as 0. And of course, -1 also does the same. For -1 also, we have final states -1, -1 or 0. Similarly, if you have a negative value of mu, that is mu equal to -1, then again also all you can have is plus or -1 going to ±1 or 0. 0 can go to all three values, but there cannot be a transition like 1 1 going to -1 or -1 going to 1. This is what we call, this is what we have termed as extreme switches. So this particular model, although quite studied and so on, cannot uh, allow this kind of switches. And again, there can be instances there where this happens, that you switch from one extreme opinion to the other opinion, or you can go through the transition, you can have a very quick transition through the zero state, but that happens in a very short time scale. So essentially you go from 1 to -1. But this particular model with mu equal to ±1 cannot capture that feature. So therefore, what we do is that we change the value of mu in such a way that now extreme switches are possible. That is, +1 can go to -1 and vice versa. Now, please feel free to ask me any question in between. There's no problem. Okay. And let us now consider the model which I am going to discuss today. Here we have mu equal to mu can have values both +-1 and +-2, but we have the same probability p for negative values. So only one parameter is there, but the mu value has now more possibilities. So now if you go through the same procedure, you can see that the +1 can go to +1, +1 as well as -1. And again, -1 can also go to -1, -1 and +1. But 0 can go to +-1 as well as to 0. So now switches from 1 to -1 and vice versa are possible. So we are going to study this model and in this talk we are going to discuss some results. So our aim is to obtain the mean field dynamical equations and their solutions for both cases where this p, remember this p is the probability of negative opinions when p is equal to 0 or non-zero, and order disorder transitions and associated exponents, then something called exit probability, time scales, dynamical exponents, etc. If I have time, then I will also discuss some results, very recent results on the two-dimensional model. Sorry, I forgot to mention something. Now, this mu is equal to +-1 and +-2. Both values are possible, but there is also another parameter which we introduce here. This parameter is Q, which determines that whether what value will the absolute value of mu will be decided according to Q. So it's not written down here. Let me tell you that mu can be +-2 with probability Q. So the original model has Q equal to 0. If you have Q equal to 1, that means mu is just +-2. +-1 values are not allowed. So we just construct the transition rates in this manner. There's no need to go through all these details. So finally, there are three variables. We have F0, F plus and F minus as -1 as the densities with opinion 0 and +-1. Okay. And three variables, but they together equal 1. So therefore, we only need to have two independent equations. And these two equations have been written down here. df plus dt, they depend on q in this manner. P is taken to be 0 in case 1. Now one can also form the order parameter equation, the rate equation for the order parameter. This is very simple. It is simply f0 into ot. Now, if you think of steady states, then one can of course have a steady state with O equal to 0. And the other steady state, if O is not equal to 0, can be achieved if F0 equal to 0. But if we have a disordered state initially, then we cannot go to an ordered state because of this equation. that then at t going to infinity, the steady state can only be where O is equal to 0. The average value of O is again equal to 0. Okay. Now here we also have another kind of fixed point which we have called the frozen fixed point. For all values of q, we see that there exists a non-trivial disordered fixed point at which there is no evolution of any of the individual densities. Why do I differentiate this with the other fixed point? The fixed point can be where the order parameter has reached a fixed value, but the order parameter can reach a fixed value with the other parameters, that is f0, f plus, f minus 1, having multiple values. But the case where all these values are fixed is called the frozen fixed point. So if I now consider the disordered frozen fixed point, that means in the disordered state f plus and f minus will be equal. So let us call that x. Then one can form an equation for x which looks like this. So there is a trivial fixed point which is x equal to 0, of course, but there is a non-trivial fixed point which is given by these equations depending on q. So next we do the linear stability analysis, and now we take initially ordered state. So we move a bit away from the frozen fixed point. So now f plus is x star is the frozen fixed point. So we take x star to be f1 to be a little bit larger than f minus 1. So there is this is biased. So it has a it is ordered initially, and then the linear stability analysis gives you the equation for delta t, and we see that it goes exponentially with alpha q like this. So delta t essentially grows until and unless alpha is equal to 0, which can happen for q equal to 1, and that is a very interesting case which we are going to discuss separately. So we see that for any initially ordered state, the order parameter grows exponentially, but it cannot exceed 1. So finally it will reach the consensus state. So we also did some numerical estimates, and we saw that this exactly follows this equation, 1 minus q and 3 minus q. Now what happens if we have an initially disordered state? So initially disordered state means that we take f plus and f minus to be same, and now we have this parameter rho, and this rho t now undergoes this evolution like this, and see there is an exponential minus t factor. So that means that rho t will go to 0 ultimately. So therefore any disordered state will ultimately go to the frozen fixed point, which acts as an attractor for any initially disordered states. And the order parameter vanishes exponentially. Not only that, this vanishes exponentially without any dependence on q. So what we did next was we numerically solved the differential equations for some typical initial conditions and found out what are the results. So if we take q equal to 0, which means the original BCHS model, then we have chosen 4 sets. You can see that one is a disordered state which actually corresponds to the FFP for q equal to 0. This one is another disordered state which is not the FFP, and these two are disordered states with the initial value of O finite. One is finite and the other one is finite but very small. So you can see that the disordered states will ultimately, this is the order parameter. We have plotted all the quantities, but if you look at the order parameter, it essentially gives you all the information. So for q equal to 0, you can see two sets, they are going to 0 because they were disordered states, but the other two states, they are going to the consensus states. Now, if we take any other value, not q equal to 1, the results are very similar. So for initially ordered state, as we already discussed, delta t goes exponentially like this. And this tells you that the magnitude of the order parameter increases. So if we go back to the order parameter equation, then you see that in order that the order parameter has a finite value, then f0 must be 0 at the steady state. So we can put f0 equal to 0, and then we have only one variable because now f0 equal to 0, so f plus 1 is y and f minus 1 we take as 1 minus y, and then we get an equation for dy dt. Then f plus can only be 0 or 1. So this is the steady state. So for any q not equal to 1, it is a consensus state, and that is why we get results similar to q equal to 0, that is a consensus state all the time, provided the initial state is is ordered. But as I told you that q equal to 1 is a special case, and there alpha is equal to 0. So this suggests that there is a kind of conservation of the ordered parameter. Okay. So let us see what the numerical solutions of the differential equation gives us. It's not exactly a constant, but very soon we see that after a few steps, all the values take a fixed value. Okay. Now actually what happens that f0 goes to 0 very fast, you can see here, and then we can say that it is a quasi-conserved model, because after that when f0 becomes 0, everything becomes constant. And if we take f0 equal to 0, why I am saying so, it is justified like this, then you see the equations for df plus 1 and df minus 1, it becomes essentially equal to 0 if we put f0 equal to 0. So f plus f minus 1, they all become constant as is shown in this result. We have also made done some simulations, and these simulations, in these simulations, since it's a finite size, we know that a random fluctuation can drive the system to a consensus state, whatever is the value of q and whatever is the initial conditions. So we see exactly that all the sets for all the sets we are getting a consensus state, even for the q equal to 1 case, but the way it goes to the consensus state is different for the q equal to 0 case or any q not equal to 1. As we have already shown, it's exponentially fast, but for this we can only get results from the numerical simulation. It is approximately t to the power half, which means it's much slower. We can also compute the consensus times, and the consensus times also show that q equal to 0 and any q not equal to 1 and q equal to 1 are quite different. For q not equal to 1, the consensus times are scale as log n, which means it is a very fast process, while for q equal to 1, tau is varies as n, which means it's very slow. Now there is another quantity which we have computed, which is called the exit probability. Here what we have done, we have again started with a bias state, then f plus and f minus 1 are chosen to be in this form. So delta is our parameter here, which if delta is 0, it's of course an unbiased state. The exit probability is a function of delta, and it's the probability that the final configuration has f plus equal to 1. Now one can calculate it from the numerical solution of the differential equation once again and use this relation. And if we do that, then look at these figures. Then we have E delta with as a function of delta to be a step function for all q not equal to 1. For q equal to 1, it is just like a straight line, which is like E delta goes as delta. The numericals, the simulations also give similar results. For q equal to 1, we see that it goes as roughly E delta goes as delta. And also, interestingly, it is size independent. So for different system sizes, it has the same result. And from the numerical simulations, of course, they are finite size, so they will not show this step function. But we'll see that the individual for the individual sizes, this thing goes to a step function, but we can actually collapse this data to this form and obtain the form of the scaling function done numerically just by fitting the scaling function. We see that it is dependent, it is determined by a parameter lambda. The lambda actually depends on q. But all other things like this parameter nu bar which is appearing here, it doesn't depend on q. Now let us go back to the q equal to 1 case once again, and we'll establish that it is actually equivalent to the voter model. How? Here we have seen that f0 goes to 0 very fast, so effectively we get a binary opinion model. And transition rates for f0 equal to 0 are identical when f0 equal to 0. They are identical to those in the voter model. We can just put f0 equal to 0 and obtain this result for transition rates from 1 to -1. And like the voter model, so here the agent adopts opinion of the other agent with whom she interacts, irrespective of her own opinion. And it also shows the conservation, although not exactly conserved, but quasi-conserved after a transient time. And this is similar to the voter model in any dimension. Remember, this is a mean field model. So here also we find similar behavior. And the exit probability is linear, which is actually a result of this conservation which occurs in the voter model or in the Ising model in one dimension. And also there is another feature that there is no finite system size dependence in both. And lastly, the consensus time is proportional to n for q equal to 1. This result is also true for the mean field voter model. So we conclude that q equal to 1 corresponds to a mean field voter model beyond a transient time. So after this, I'll move over to the other case, which is when p is also not taken to be equal to 0. Remember, p is the fraction of the negative opinions we have here. So here we now have two kinds of disorder. One is due to p and the other one is q. Once again, for both mu equal to 1 and 2, probability of negative values is q, and probability of this mu equal to plus minus 1 is 1 minus q, and probability that mu is equal to plus minus 2 is q. Now the non-limiting case is p equal to 0, which is the just discussed case, and q equal to 0, which is the BCHS model, which shows an order disorder transition at PC equal to 1/4 with mean field Ising criticality. Now I'm not showing the transition rates once again. We have more equations now, and not more equations, but more variables now. So the equations are quite long. And finally, we obtain the equation for the order parameter, which goes like this. Now, once again, we have the same result, that if we have start with a disordered state, when we will get a disordered state finally. Okay. Now, when can we get a steady state with order? When this quantity, so right now I'm going to the limit in case q equal to 1, because q equal to 1 actually showed that there are lots of interesting results. So for q equal to 1, this quantity which we had in brackets in the last equation simplifies to this version. And for an ordered state to exist, therefore f0 has to be equal to 2p. But as I already argued, even when p is present, p is non-zero, this f0 goes to 0 very fast, because the equations show us that, the transition rates. Okay. And this is because physically what is happening, the transition to the 0 state is rare, because the +1 and -1 states are going to -1 or +1 in the extreme limit q equal to 1. So very few transitions are happening to a q to a opinion equal to 0 state. Okay. So now let us assume that there is a particular time after which the f0 becomes 0, and we shift the origin of time there. It doesn't really matter, because finally we are interested in the t going to infinity limit. And then the equations become simpler and they can be solved. The solution is like this. So when p is equal to 0, the only solution is that f plus minus is just equal to half. And that value means that it is a disordered state. But if p is not 0, if p is not 0, then it is half, because if p is not 0, then this exponential factor goes to 0 very fast and we are left with a disordered system. Only when p is not equal to 0, we can have a finite value, which we already saw in the last case. So what happens here, if you look carefully at these two equations, this is just a model in which we have a binary value of the opinion or spin or whatever you say, call it, and it is just randomly flipping with a probability p. You look at the equations, so it is just giving you that result. So it's not a surprising thing that it is ultimately going to a disordered state. So let us now discuss the case for q not equal to 1, when we have the same equation now, and now we have a steady state t going to infinity, where f0 will be given by this. The moment you have f0, you can solve the other equations. Finally, a complicated equation is coming for O, which is a function of both p and q, and we can again get a frozen fixed point. Interestingly, it is exactly the same which we had, independent, so therefore independent of p, and then we can find out for the order disordered phase boundary by putting these values, and finally we get a equation of a straight line. And actually this order disordered line can be obtained in a different manner, which I am going to tell you in the next slide. So this is our order, this is our phase diagram. We have, this part is the ordered part and this is the disordered part. Okay, and equation to this phase boundary is like this. And here I have also plotted f0, which is given by this equation, because this is just a function of q only. And we have also found out what are the exponents. The critical exponents again show that they are the mean field exponents, independent of the value of the q, value of q. and whichever direction you take in the phase diagram, you can see that we can go like this or this. The critical exponents have the same value, so it is universal. We have also done numerical simulations to show the to get the critical exponents. Okay. Now, as I told you, the phase boundary can also be estimated from the stability of the frozen fixed point. So we have again this ordered parameter is proportional to e to the power some gamma t. But now gamma can be both negative and positive, and exactly where gamma is equal to 0, we have the phase boundary. And we can also obtain the time scale. The time scale is tau equal to gamma inverse, and this diverges at the critical point, and this is familiar critical slowing down. Once again, I just show you the numerical solution from the differential equations, and this shows the growth and decay of the order parameter in the ordered and disordered phases. Now, if we consider, so we get one time scale from here, which is this. Another time scale we can obtain if we have a relaxation. Sorry, if we consider the relaxation from a perfectly ordered state. So this is studied numerically only, and solving the rate equations taking initial condition equal to 8 plus. Sorry, it is again from the differential equations, numerical solutions. Initial condition is f plus 1 equal to 1, and the general behavior is given by this very well known thing. And so we get another estimate of this of a time scale, and of course there is only one time scale in the system, therefore tau r and tau, they both follow the same kind of scaling behavior, that is the epsilon to the power minus 1, where epsilon is the deviation from the critical point. Now, exactly on the phase boundary, one can also find out what is the behavior of O. Here, it will not be an exponential decay, but it will be a power law decay. The exponent is close to 0.5. And remember, we obtained tau is proportional to epsilon to the power minus 1. And we have from scaling arguments that tau is proportional to epsilon to the power minus nu z, but z is the dynamical exponent. So one can argue that nu z is equal to 1 here. And we know that the scaling behavior obeyed by the order parameter is in general like this. So exactly at the critical point, we have t to the power minus 5. So arguing in this manner, y should be equal to beta by nu z, and therefore y should be equal to half, and that is what we have obtained. So everything comes consistently, and these are the results. So basically, this Q does not have any effect on the critical behavior. It can only make the critical point different. May I know how much time I have left? Excuse me.
Yeah, you have about 2 minutes.
Hello?
You have about 2 minutes.
Hello? Can anyone please tell me how much
Yeah,
time I have?
you have about 2 minutes. Can you hear me? 2 minutes plus question.
Am I there?
Yes, yes. Can you hear?
Yeah, I can hear.
You have about 2 minutes plus question.
2 minutes.
2 minutes plus 5 minutes for questions. Yeah.
Okay, okay.
Yeah.
So I will not go into the details of the last work, which is actually not yet published. So essentially what we did is we also studied the two-dimensional BCHS model for both P and Q not equal to 0. And we obtained the phase diagram using two different methods. One is mapping the whole thing into a walk, and the other one is a standard thing that is doing finite size scaling and so on. So I will just show you that this is the phase diagram which we obtained, and once again the behavior is same in the sense that we again get back the two-dimensional Ising model exponents everywhere, and uh, the critical behavior is therefore unchanged. But only thing is that we get a new exponent here because we have computed. I cannot go through the details right now. We mapped to the whole thing to a walk, and this walk, if we take the distribution function, that is what is the probability that the walker is at the point x at time t, then the distributions actually change their nature at the critical point. So this is how one can find out the critical point. It goes from a unimodal function to a bimodal function. But if you and essentially you know that it is expected also that in the disordered phase these distributions become Gaussian. So these Gaussian distributions, if we now take the width of these Gaussian distributions in the disordered phase, then that width shows a divergence at the critical point, and the corresponding exponent with sigma of the distribution. Here you see these are the distributions in the disordered phase. It shows a critical behavior like this, a power law behavior, and this kappa we cannot connect to the already known exponents, and it is universal. Once again, it's not dependent on P and Q, and it might be a new exponent. We still do not know. Okay, so I will now go to, I will not go to the details. These are the finite size scaling analysis. The results agreed very well, the two methods. So let me go to the concluding part. So in conclusion, we have considered a three-state model which admits negative interaction and extreme switches, and we see that when the negative interactions are the negative interactions are the relevant variable in a sense, because they are responsible for driving the society from a consensus state to a disordered or polarized state. Extreme switches introduce an extra noise, okay, but it doesn't affect the critical behavior, but it does change the critical point, as I already told you. With the extreme switches, F0 decreases on the phase boundary, indicating a stronger polarization. In fact, in the disordered phase, it is shows us very strong polarization as Q is made larger. For the maximum extreme switch, there is a random voter model-like behavior, and any finite fraction of negative interaction makes the system disordered because it becomes a binary model with random flipping. And the critical behavior, as I told you, is same as that of the Ising model. Here I might just mention that there are some debates on whether the PCHS model has the critical behavior of the Ising model in all dimensions. It's not yet established, but at least for two, in d equal to 2, and for the mean field case, we found that the critical behavior are same. And finally, the walk picture shows the existence of a new exponent, and which has to be explained. And sorry, and finally, I must thank the financial support from ACRB, Government of India grants, and thank you very much for your attention.
Yeah. Thank you, Parangama. Yeah. So I think we have a few minutes for questions. Yeah. Yeah. Any questions? I have a question.
Yes.
So you have this case where you go to this ordered state, right? Where you basically form an opinion.
Yes.
Right. So can you just physically tell like what is the situation when you go to this order state? I understand in terms of this F0, etc. But like,
Basically, the order is measured by the average opinion, and you can see that the zero opinion does not contribute in the calculation of the order parameter because it's a sum of all the opinions. So you just see that if the sum is not zero, then you have some emergent behavior. So that is what we call the ordered state, just like in a speed model.
Mhm.
On the other hand, if the +1 and -1 they are equal, or in the extremely rare case when everyone has become zero, then also it's a pseudo ordered state, but we call it an disordered state because the order parameter itself is zero.
Mhm. So there is no scope of forming opinion starting with a no opinion state. Like, I mean, in society, sometimes as time evolves, we tend to form opinion even if we don't have opinion at the beginning, I guess, right?
That's what we
Uh,
almost in all the cases we
okay.
started with the average opinion, like average opinion would be very close to zero.
Okay. Yeah. Okay. Yeah. Thank you. Yes.
We have a question for the online people. Rafael Barrio.
There is a question from the online people. Can you see it?
Yeah.
How do, can you tell me how does it?
Just open your mic.
Just I think you have to open the chat. I think.
No, the chat box. In the chat box, I can only see messages from the organizers.
Yeah. Can you just open the question? Then I can read the question maybe. Yeah. Maybe you can just ask. Yeah.
Can you hear me?
Yeah. Yes. Yes.
Thank you for opinion and social behavior. I mean, but the model that you presented is more or less an icing model, yeah, or a spin model. What is the relationship between them and the social behavior?
Okay, let me tell you, the answer will be a little bit long. First of all, you see there is no Hamiltonian here. In Ising model or other spin models, we have a Hamiltonian. This is completely a dynamical model. We don't even know whether a steady state or a will be reached or not. Like equilibrium is not really defined. It's a non-equilibrium model. Okay, and the thing is that some of the applications which we did with this model, let me also add that very few opinion dynamics models have been actually applied for real situations. Of course, Professor Galam is there and he has lots of applications done with his models, I know that. But otherwise, the examples are not many. So in this case, we could actually explain some of the real situations like the US presidential elections and also Brexit using this model. And we compare the results obtained from IC model and this VCHS model. And the VCHS model gives a result which is closer to the reality.
Thank you. That's it.
Okay. Yeah, so okay, if there are no more questions, then let's thank the speaker again. Yeah, thank you. Yeah, thank you, Parangama. Yes. Okay. So now we go to the next talk. Is it is Ah.
Can you ask to Galam to start to share the screen?
Yeah, so the next talk is by Serge Galam. Can you please share the screen?
So, okay. I got that I can.
We can see you. I think yeah, on the left there is a button. Yeah, I think where you put your cursor. I think on the left. In the down, there's icons. I think there's a button for sharing the
I
screen.
see what you told me, but it doesn't, but not okay.
This is the screen here or there?
Screen.
This screen here. Okay. So this cursor is here.
Yes.
That cursor. Okay. Can you see the this all the icons at the bottom of the screen?
Yeah, yes, and when I click on it, it told me he can't do it.
I think you have to give the permission.
Okay. I have to authorize, so let me how to authorize.
Yes. Listen. Can you try now?
Maybe I should turn down and connect again. What do you think?
Yes, but I
Yeah, maybe try. Yeah, maybe just try it. Yes.
Okay, let me try. I
Yes.
quit and I
Is it connected? Yeah.
Once he connect again,
Uh-huh.
I will present by my laptop
Uh-huh.
and I will move the presentation. Can you say that?
Yes, we can see you now. Can you hear us? Okay, so yeah, we can see the presentation here.
Okay, great.
Yes, 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 yeah.
Okay, so sorry for, and I can move it.
Can you just check if you can you go to the next slide? Let's see. Yeah, it is changing. Yes.
Okay.
Okay.
So you'll do it for me because I don't have the
Yes, yes, yes. It's doing from here. So maybe you can just tell that next slide or something like that, and we'll just move to the next slide.
Okay, so sorry, actually I wish I would be there with you and we will not have this problem. So I will discuss about polarization and to define it very simply is to say that polarization define, okay, so it's a multipole and yeah, the second one, please.
Okay.
Next one. Polarization defines a political state of a society divided in two groups, more or less the same size, and which are radically opposed, and usually they are also sharing some hate between them. And this is a very important element. So it is today a major threat to most democracy, especially we can see it in the US, in Brazil, in Israel, in France currently. So can we find what are the underlying mechanisms? Next slide. I will study this problem using the so-called Galam model of opinion dynamics, which deal with two competing discrete opinions, A and B, and I consider heterogeneous agents with three different psycho. I will have floater, contrarian, stubborn, and the distribution of tie-breaking prejudice. Next. A floater is an agent which do have an opinion, advocate for it, but it is susceptible to shift opinion in case you give more convincing argument that the other opinion is better. So he know why he is A or B, but he can shift from one to another. A contrarian has an opinion, however, he does not like to be like the other. So if he is in a group where everyone say A, even if he was thinking A, he will move to B. So he shifts opinion independently of the opinion itself. A stubborn is an agent who will not change opinion whatever argument you give it to him. He is stubborn, inflexible, he never shifts. And then tie-breaking prejudice will be defined later. Next. So I consider two mechanisms. One external, which act directly on the agent to make pressure to select opinion A or B, like media, leader, external event. And then there is an internal event which results from the interaction among the agent. I will study the second, the internal mechanism. Next. So then to start the modeling, I say that at some point I cut off the external pressure and I make a measurement of what are the respective proportion of people supporting A and B. I call P0 the initial proportion of agents supporting opinion A and 1 minus P0 agents supporting opinion B. Everyone has an opinion here. And then I now start the internal mechanism that people start talking and exchanging among themselves. So let's now study this dynamic. Next. So how I do it? I take into account that when we have a campaign, like now we have an election, very important in France going on, people discuss a lot in informal meeting. And this informal meeting usually gather only few number of people, 2, 3, 4, 5. They discuss and eventually some people will shift opinion. This is very complicated phenomena. So here I make it simple, saying that this simplicity could capture what happened in reality. So of course, this is a strong hypothesis, but it will account on average of what is happening. And then this hypothesis is to say, I make it within the group as if it was a vote. All the discussion came down as every agent which is discussing is having one vote, and I use a local majority group, which means I have 3 people which discuss together. They arrive with an opinion A, B. Everyone gives his opinion. After the meeting, the person which was minority here sharing B will shift to A. So this rule will create local group polarization in every small group of people which are discussing. It does not apply to stubborn, which will preserve their own opinion, and contrarian will shift opinion afterward. Next. So here comes the tie prejudice point, because majority rule work well. However, when I have even size, a pair of 4 people or 6, I may have a tie. And then at a tie, local majority does not apply. Usually in physics, we will say we take a probability half-half to go in one direction or another, or no one change opinion. Here, as we are dealing with human, I am introducing an extra hypothesis, which does not occur in physics, saying that indeed, when I have a tie, it is equivalent that the group is doubting to which opinion decide to select, saying that you have as many arguments in favor of A that in favor of B. So the group is doubting. And at this point, I say that then, as the group is doubting, there is an unconscious tip to the leading collective prejudice in the group. People don't have to express it. They just say, okay, let's toss a coin, A or B. But the coin is biased according to their internal prejudice. So then, to account for the distribution of this internal prejudice, depending on the issue, I will say that in a given group with 2A, 2B, I will deal now with a group of size 4, the probability K is that this tie will end up with 2A and 2B, 4A, and 1 minus K that it will go to 4B. Next. So now to implement the dynamics, I randomly distributed my agent in small group. Second, they are locally updated following majority rule. Contrarian shift opinion. Then agents are reshuffled and distributed again in small group. And the above cycle is repeated several times, 1, 2, 3, 5, as many as we want. Next. To monitor the process, I will now write an update equation. So the initial conditions are given by this P0, which is the initial proportion of agents supporting opinion A. Little a is a fixed proportion of stubborn which are having opinion A, which means that for opinion A, the floater, the proportion is P0 minus A. And then I have for proportion B 1 minus P0 with small b proportion of stubborn, and then 1 minus P0 minus B proportion of B floater. The proportion of contrarian is little c, and the tie-breaking prejudice is K and 1 minus K. Therefore, each cycle which I just described before will modify the proportion of A going from P0 to P1, P2, P3. Let's calculate this. Next. An important remark is that the model apply to different communities, and I define the social communities by integrating all the people which could, along the campaign discussing an issue, could meet together in a small group. And then we will have separate social community, and the dynamic will be parallel in each one of them. Now, this community can be defined with different initial conditions, different proportion of stubborn, of contrarian, and also different initial proportion of A. Next. Then now I study what happened in a given social community. To write up the update equation using my local majority, I can have the equation which is written here. It looks a bit complicated, but actually it integrated all the configuration which we can get for a distribution of 4 people, and with all our parameters P0, A, B, C, and K. What is interesting that this allows to make a lot of analytical calculation. And then now to find out the dynamics, I have to solve the fixed point equation P1 equal P0, which will determine the attractor and tipping point. Next. So as the equation is complicated and we have a multidimensional space, I will now look what happened to the dynamic within special subcase of the full landscape. So let's see first what happened when I have only floaters, which mean agents which shift opinion depending on the local majority. I have no stubborn, no contrarian. When I solve the fixed point equation, I find that I have 2 attractors, which are 0 and 1, and a tipping point, which can be either at 23% up to 77%, depending on the type prejudice. However, what matters here is that in all cases, one opinion will become unanimous if I have enough update, which means if the campaign lasts long enough that people discuss and discuss again and discuss again, at the end, everyone will share the same opinion, either A or B, and this depends on both the initial condition and the value of K. But the process is democratic, and we got one-side polarization. So this is the first aspect of polarization. So everyone is sharing the same opinion. Next. However, what is important to say that, as I mentioned before, that we have parallel dynamics in different social communities, then we can end up with different community ending up with polarization either along A or B. So we can have either identical one-side polarization or opposite. If it is opposite, this defines what I call a segregated polarization, which means every social community is coherent and aligned along one opinion. However, the one nearby will be the same but on the opposite opinion. So this creates strong opposition, and here we have a basis for the eventual development of hatred, but between communities, because they don't exchange, and everyone within the community shares the same opinion, but which is different from another community. Next. The second case now, I introduce some contrarian in the first case. Now I have floater and contrarian. No inflexible or stubborn, no tie breaking. I will take K equal half, which means the prejudice are divided equally in favor of A and B. So in this case, the 2 attractors now will move from 0 and 1, and they will be located with a well-defined majority coexisting with a minority. So we have no polarization here, no problematic. However, when you look up at the equation, we find that this situation exists only when the proportion of contrarian is lower than 17%. When I get higher, the dynamic is turned upside down, and go from a tipping point dynamic to a one single attractor, which is located at 50%. Next. Which means when I have more than 17% of contrarian and all the other agents are floater, whatever the initial condition, the single attractor 50-50 is reached. And this will give us a two-side polarization. We have two groups, same size, opposite opinion. However, if I look at the agent level, at the microscopical level, I keep having shift between A and B, which means while collectively the situation does not move, at the individual level, people shift opinion, which means we have a fluid polarization. And then as we have a fluid polarization, people sometimes has been A or B. This has no basis for hatred and rejection because people know and sometimes even have shared the other opinion. So we have a kind of acceptance of the other opinion. Next. Now let's go to the more problematic case, when I have floater and stubborn. First, then I will define, to see how it works, three subcases. The first one, I will have stubborn only on one side, let's say opinion A. If the proportion of this stubborn is low, I have the picture, the dynamic flow, which is shown above. And then I have an attractor at 1 and another one which give me a coexistence of majority and minority and a tipping point which is below 50%. So there is here an advantage to opinion A due to his stubborn. However, I will move smoothly toward one side polarization if the initial condition allow it. Otherwise, I will have a coexistence of majority and minority. However, again, I got here one side polarization, so no basis for hatred and rejection. But as before, we have here some limit at this picture. Solving the equation, if I increase the proportion of stubborn on side A and I go beyond 17%, then again the dynamic move from a tipping point dynamic to a one attractor, single attractor dynamics. But now it is not located at 50-50, it is located at 1. Next. Second case, now we put stubborn on both sides, but on equal proportion. So the picture of the flow dynamics now is symmetrical. So the tipping point is, for low proportion of stubborn, is at 50%. And on each side, now I have a coexistence of majority and minority. So there is no polarization here. However, again, if I increase the proportion of contrarian, but now to a higher value, it's 22%, then I will move again toward two-side polarization because it will go to one single attractor located at 50-50. At least here we recover the 50-50 attractor as with contrarian. But while for the contrarian, it was fluid with people keeping moving between A and B, here it is rigid. People don't move between A and B. Because already to get to this picture, we need to have at least 44% of stubborn among the population, which is a lot, and then it may even increase. So this is a really basis for hatred inside communities. This is important. Before, we found hate between communities. This is inside communities due to the existence of stubborn A and B. Next slide. And this is the most general case with stubbornness because I will have different proportion of A and B stubborn. And then I will get, depending now on which opinion as more stubborn on its side in order to win, because the attractor, the single attractor, is not going to be at 50%. It's going to be at a higher or lower value than 50%, depending on this additional stubbornness on a given side. However, this gives us again two-side polarization, which is rigid, but now one group is a little larger than the other one. And again, this is happening within a community, and this is a basic, again, for hatreds inside communities. So the main conclusion at this moment, of course, the real situation, we need to solve the problem with having altogether stubborn, contrarian, floater, K. But as I say, this you will need to solve it numerically on an higher dimensional space. However, by looking to subspace, we have find out that indeed, when we talk about polarization in society, this modeling has shown that indeed we should see if we can discriminate between different polarization. One which I call one-side polarization within a community, fluid polarization among community, and these are not posing a threat to democratic society. The one which are really posing a big problem are the segregated polarization, because this is opposition between different social community which are very homogeneous inside the community but opposite to the other one. And the rigid polarization within a given within a given communities due to the stubbornness. So these are people which will fight even within their own belonging community. If you want more info, there is this paper which was published in Entropy 1 year ago. Next. So I always like to publicize this book. It's already 12 years old, but I think it's still actual. And it's worth a look, and you can have a free ebook from your library, I think. Next. So in conclusion, I would say that indeed, in all our democratic countries, we are now facing a serious problem with polarization. To dismantle this, the rigid polarization is a top priority, and we have to be able to discriminate between rigid and fluid polarization. And I think that with our social modeling and our work, we could maybe help solving the problem, at least to contribute, giving unexpected and different light on this problem. So thank you very much for your attention.
Yeah. Thank you. Yes. Okay. So we'll take a few questions. Yeah. Yeah.
Hi, thank you. In your talk, you have talked about communities, and in complex social networks, often there are communities of nodes that are connected weakly among them, among themselves. So how this model could be maybe exported or adapted to study this kind of phenomenon on a complex network?
Yes, I think that this is there is an echo. No, okay. Yeah. No. Thank you for the question. Yes, this will be interesting to apply it, and I think it should apply directly to the study of networks and having this peculiarity of the various distribution of stubbornness, stubborn type prejudice, and contrarian within different network, and see how the dynamics evolve. This would be great to do.
Thank you.
Hi. So if I correctly understand, your model is mostly mean field in nature, right? So everybody can interact with anyone, you can choose.
No. This is sorry. I just interrupt you because this is always people think, and it's natural to think a priori, but it's a different from infield for two reasons. People potentially could interact with everyone, but effectively they don't. They interact in small groups. So this create short range correlation that you will not have in a midfield. And then I repeat the process. So this corresponds more in terms of physics to a real space renormalization group of the problem and not a midfield problem, treatment of the problem.
But you choose your group from the entire population randomly, right?
Yes, but simultaneously they are all distributed and they all interact in small groups.
Okay, so now if we want to put that, if we choose the group from following a special structure like a lattice structure, because for example I can group, if I'm here I can group mostly, more probably will group with my local friends here than being in India. Okay, though it's possible in present days, but there are more probability to make the group locally where we are. So is it possible? Okay, if we apply this model following a special lattice structure, do you think the results will be very different, or they will be more or less similar in nature?
Okay, no, yes. So then this would be interesting to introduce a kind of constraint on the distribution of people in the group, if I understand this is what you are saying.
Yeah.
And I think this will maybe will accelerate or slow down the dynamics and maybe modify the location of the attractor. But it will be interesting to check. But the main dynamics will stay unchanged. But the value could be different, which makes sense if we are interested in the real situation, of course. So I think that this would be nice to do and to see how you implement this constraint dynamic. Because here, with respect to what we do usually in physics, if I take a lattice, here I am moving my agent when I do the reshuffling within a given community. So then it is on your lattice as if once I make local update, I redistribute the spin on the lattice, which we don't do usually in physics.
A small question. It has been stated that social networks which allow people with a given opinion to construct a group that only shares that opinion has exacerbated the problem. Does that make any sense to you? Or what are your comments?
Yes, thank you. This is what many people state and repeat. However, I have a different explanation of this. I don't think that people in the social community join it because they share the same opinion. What the modeling show here is that if I take a given community with a distribution of different opinions, the fact that people will discuss among themselves will bring them to share the same opinion. So it is not an echo chamber in recruiting the people. It is the fact that you belong to the community which will end up making everyone share the same opinion, but it could have been one or the opposite, depending on the initial condition. And this is a very, I think, subtle point, contrary to what we always, everyone state as if it was really granted, because clearly, if you take a social community, you find that the people share the same opinion. But my statement here is that there is an underlying dynamics prior to this showing of one opinion. It is not from the start. This is an alternative explanation of the observation of echo chamber.
There's a question from online. Can you please go ahead and ask it.
Well, more than a question is just a bit of propaganda that I'm going to make to my talk, because this was a very interesting talk, and talking about the gulch of the problem. But now I'm going to extend those sorts of ideas to this what is related to the former question, that what happens if we define the communities in a network, yeah, and so we will modify the networks, and we end up in some cases with this polarization, which is very interesting. Thank you very much for your talk.
Thank you for your comment, but I think it's worth to check and compare both approach. Yeah.
Right. So you're looking at 12, right?
Okay, thank you.
Okay, so if there are no more questions, let's thank the speaker again. Yeah. Yeah.
Thank you.
Thank you very much for your talk.
And
Yes.
enjoy being there.
Thank you. Yes.
Good for you.
Okay, so now we break for coffee. I guess, and what time we come back? I guess usual time. Half an hour. Yeah. Okay.
Hola, Hans. Hola.
Bueno, ajá. ¿Qué tal, doctor? Ahorita vamos a hacer una prueba. ¿Me escuchan?
¿Me escuchan?
Buenos días, doctor Rafael. Sí le escuchamos, pero ahorita le contacto con los miembros del staff de las conferencias.
No, yo no te oí muy bien, ¿eh? Lo único que tienen que asegurarse es que para mi presentación ustedes me dejan compartir la pantalla, ¿no?
Sí. Hola, doctor.
Hola, Hans.
Todos los participantes tienen permisos de compartir.
Ah, es que pasó un incidente con el participante pasado, ¿no? Que no podía compartir.
Sí.
¿Quieres hacer una prueba o no?
¿Puede usted?
¿Perdón?
Sí, intente compartir su pantalla, por favor.
A ver.
¿Sí funcionó? Perdone que estábamos a Sí, intento compartir su pantalla. El problema a veces es que los permisos son del equipo de cómputo del navegador.
Ah, ok. Ah, ok. A ver.
¿Puede poner esta, también subirla ahorita para probarla? O sea, moverle la computadora y ponerla acá arriba. ¿Sí? Y aquí ya le regresamos la USB. No, sí, ya bájala. Sí, sí, por favor.
A ver. Vamos a compartir.
Sí, la que acabamos de quitar es la que va justo después del break.
Ya sé. Ok. Sí, está bien compartida. Perfecto. Bueno, entonces dejo de presentar y bueno, me voy a tomar un café y nos vemos al rato, ¿vale?
Sí, doctor, muchas gracias. Nos vemos en un momento.
¿Podría probar el claro? Perfecto. Este tal vez. No sé dónde queda el otro.
Done?
Punteros normales. Gracias. Gracias.
Okay, so it's time to start. This is the pre-launch session, and the first speaker is Antonio Méndez. So Antonio, you have 40 minutes, please.
Thank you. Thank you very much for the introduction, and thank you very much for the invitation. Here, I will take the opportunity to present to you some of our recent results on a very specific application of random matrix theory to a network problem. This work, in fact, okay, this work is done in collaboration with Marisol and Gabriela, who are also here and are presenting posters. So I will give a review of this work, and if you need more details, so the posters will be there, I think today or tomorrow. Okay, now I will go to these contents. The main idea will be to try to understand some of the properties, spectral properties of a specific model of networks, which is a multi-layer network that I will introduce in a moment. Yeah, the idea is to apply some ideas of random matrix theory to this kind of problems, a network science problem in particular. Okay, I like a lot this phrase here, which was written already several years ago by Dyson, in which it is explained, let's say, the philosophy of random matrix theory with the original, let's say, motivation, which is the understanding of complex nuclei. However, I think that if we just replace this word here, nuclei, by system, complex system, so everything here applies to a very wide family of possible situations. In particular, we can apply, in fact, random matrix theory to a wide variety of complex systems or complex processes. Of course, if these systems or processes can be represented by matrices, of course. So the idea, and that's why I believe, so we have so many applications of random matrix theory in the original one in physics, in nuclear physics, but also quantum chaos later, mesoscopic physics. And now I will present a specific example of the application of RMT in network science. Now, the main idea of network science is the following. So if we have a complex system, we have probably many ways to approach them or to approach it, a complex system. However, if we can identify the agents composing this complex system and also the interactions among the agents, we can then construct a complex network or a network, right? So because a network has these two ingredients, the agents and the interactions between agents. Now, if we can do that, if we can extract this network from a complex system, so we then can try to understand the properties of the complex network or the network, and then trying to infer properties of the complex system, let's say. So what we will do here is to try to understand the properties of the complex network that in principle comes from a complex system by using random matrix theory techniques. That's the idea. Now, just to finish with these ideas on random matrix theory, so it's known that RMT describes the universal properties of complex systems, let's say, in this case complex networks, that's the application here. Also, we understand that RMT is associated with the limit of maximal chaos or disorder or maximal complexity. But also we have to take into account that RMT does not distinguish between two systems of the same symmetry. So, but this is also a good point. So if we want to describe, let's say, the properties of families of systems, as it is the case here, that we want to describe the properties of families of networks with the same properties. Now, this is, let's say, how we see this problem in general. Let's say we learn the application of random matrix theory by trying to understand the Hamiltonians of physical complex systems. When we, I mean, this is the original, let's say, motivation of the introduction of RMT in physics. And what we will do here is to use exactly the same ideas in which complex networks have matrix representations. We will use one specific matrix representation of complex networks, which is the adjacency matrix, but we have many others. We have Laplacian matrices, distant matrices, incidence matrices, and very variants of all of them, and combinations. And what we will do is to use random matrix theory to understand the properties of those adjacency matrices, which in principle, if we understand the properties of the adjacency matrices, we can infer properties of the complex networks, and also we can infer the properties of the corresponding, let's say, complex system, which are represented by these networks. Okay, so since we will work with adjacency matrices, here's the definition of the adjacency matrix. So if we have a network, let's say, which is composed by n agents, and we have the interactions between the agents, the adjacency matrix will be an n by n matrix whose elements are given by this rule here. So the elements of the adjacency matrix will be 1 if there is an edge or interaction or connection between two vertices, two agents of the original network, and will be 0 otherwise. So just to make sure that we have this definition clear, for example, here we have a network of 5 nodes. They are labeled with letters A, B, C, D, and E. So we label the columns and the rows of an array, of a matrix, with these letters here, and put ones where we have connections between the nodes. For example, the node E is connected with the node D, so we put a 1 in the entrance ED, but also in the entrance DE, because in this case, this network, this graph, also called, is undirected, which means that the edges or the connections are bidirectional. Here, we don't specify the direction of the let's say, flow of information between agents. However, we can also have the case in which a network, the edges or the connections in the network have a definite direction, and in this case, we call this network a directed network, which is the subject of this presentation here. In this case, so since there is direction in the flow of information between nodes or agents, so the adjacency matrix is not symmetric, and then so if we want to diagonalize it, for example, it will have complex eigenvalues. That's the main difference, let's say, between these two situations. However, I would like to say that in many realistic applications or many realistic complex systems, the most common situation is where the network is directed, where there is preference in the interaction between agents. So here I have some examples of adjacency matrices. Here we have well-known, let's say, examples of networks. 6 different examples. All of them have 25 nodes. However, the rules of connections between these nodes are completely different, or different, let's say. And this figure, I think it's very illustrative because it gives us it shows us that in fact the adjacency matrix, which is down here, has lots of information about the structure of the network. For example, in the case of a regular network, here the nodes are connected just to first and second neighbors. This network produces an adjacency matrix which is also regular. This regular network produces a adjacency matrix which is also regular. While, for example, let's say perturbed regular network produces a perturbed regular adjacency matrix too. Also, for example, if we have networks which are random, the corresponding adjacency matrix will also have random properties. And for example, if we have networks, we have communities which are modular or hierarchical, so the corresponding adjacency matrix will also have these properties. So if we can understand study and understand the properties, structural and spectral and other properties of the adjacency matrices, in fact, we can have lots of information about the corresponding networks. That's the message of this slide here. So the main network that we will study in this work here is the multi-layer network. A multi-layer network is a network which is composed of smaller networks, let's say, in which these networks have, of course, agents which interact among them inside the layers, but also can interact between the layers. That's the idea. Now, however, also there are many ways in which these nodes inside the layers can interact among different layers. And for example, this construction, a multi-layer network, can be used, for example, to model social networks. This is a very popular model in that area. But also, for example, can be used to study the temporal evolution of networks, because each of these layers can be thought as a network at a specific time. So if we collect, let's say, or we trace the evolution of a network, we can arrange the same network in different times and see it as a multi-layer network. Okay. Now, specifically, we will use these two setups. One is the multi-layer setup and the other is the multiplex. In the multi-layer, we consider layers connected in series, which means that even though we have that in each layer, the nodes can interact, the agents can interact. But for example, if one of the nodes of this first layer wants to interact with the nodes of the third layer, it has to go through the middle layer. So in this case, the multi-layer is a setup which has these layers connected in series, right? While in the multiplex case, all nodes can see all the other nodes in different layers. Now, the main property of these two setups is that the complete adjacency matrix, the adjacency matrix of the complete network, is a banded-like matrix. That's the main property of these two setups. Here, for example, this is the adjacency matrix of the multi-layer setup here, the one which is in series. And these A's here are matrices, are in fact the adjacency matrices of these layers, of individual layers. So in this case, we have M layers composing this multi-layer setup. And these C matrices are matrices that connect contiguous layers. Is there a question there? No? Yeah.
In case, I would think why would you still have layers? Because everyone is interacting with everyone else.
Sorry again.
In the multiplex case, why you do not have a single network? Because everyone is interacting with everyone else. So what is the difference between?
Yeah, that's right. Yeah. The point is that by arranging the layers in this way, so we are able to scale the properties of the multiplex. That's the main idea, which is part of the results I will present in the future, in the next steps. Otherwise, if we don't detect, let's say, the main band of the matrix, so we don't have that parameter, which is the effective band of the model, the effective interaction length of the model. That's the main idea. Okay, so the idea now, then, if we want to apply, let's say, random matrix theory to study spectral properties, which is what we will do about these two setups, we would like to replace these adjacency matrices, right, by ensembles of random matrices. However, one step before that, because these matrices are already very special because they are not so common, they are not so general. For example, even though this matrix here, up here, is a banded matrix, these are blocks. So this is a block banded matrix. It has structure. It has a more complicated structure than, let's say, a standard random matrix ensemble. And this one here has a structure which is a bit more complicated. So we will then go one step before defining the, let's say, corresponding random matrix ensembles for these two adjacency matrices. And we will go first to review the results of a work by these colleagues, Casati, Molinari, and Israelev, who introduced in this year already quite long ago this random matrix ensemble, the Hermitian banded random matrix ensemble. They didn't call it Hermitian. However, I put here Hermitian because later we will use a non-Hermitian version of this model here. Now, our colleagues here used this model as a motivation to describe quantized chaotic systems, in particular Hamiltonians, the Hamiltonian of the kick rotor, and also quasi-one-dimensional disordered system. That was the main motivation here. However, as we can see, so these banded matrices can also be applied to the study of random networks. Now, here, this is the main, I think, the main slide of this presentation, because it is the one that has all the information we will use in the future. And this is here we summarize all the results of the paper by our colleagues before, that I presented before. Now, the idea is the following. So our colleagues define the Hermitian banded random matrix model as an ensemble of n by n real symmetric matrices with Gaussian random variables inside the main band with a size B. So this random matrix model has two parameters, the size of the matrix and the bandwidth. Outside the bandwidth, all the elements are equal to 0. It's a complete full banded random matrix model. Now, they study the scale localization length, which is given by this beta here that we will keep through the complete presentation. This beta is defined as the exponential of the normalized Shannon entropy of the eigenfunctions of the Hamiltonian matrices defined here. Of course, they are normalized to the entropy of the GUE because this is the reference ensemble, because this is the Hermitian version of the banded random matrix model. And what they found, which is very important here, is that they found that this quantity beta, the scale localization length of the eigenvectors, is a universal function of this parameter here. So after a scaling analysis, they found that this is the important parameter of the system, which means that even though originally the model is defined by these two parameters, n and b, in fact, all the spectral properties depend only on this ratio here, this x new variable, which is defined in a non-trivial way as b squared over n. Now, in addition, our colleagues found that this beta depends on this quantity x, which is the scaling now parameter of the system, as this quite, let's say, simple function here. So this is the numerical verification of these statements. So here it is plot x as a function of beta as a function of x for several combinations of matrix sizes and also bandwidths. And as you can see, all the points fall on top of this curve here. And this is very important because you see, if you want to make, let's say, a prediction about the localization properties, or you want to design, let's say, if you have, for example, a wire, which is one of the applications they use, I mean, to propose this model. If you have a wire which has some, let's say, localization properties which are around here, and you want, for example, to push, let's say, the eigenfunctions to be a bit more extended, to have more, for example, in this disordered wire, more conductivity. So you can move this parameter x in several ways, because there is a combination of the two parameters here, not only the length of the wire, but also the width of the wire. Okay, so these kind of results, these scaling results, are very important because you can identify the single parameter of the model, the important parameter of the model, which is a function of the original parameters, of course, but also because you can also predict and manipulate the properties of the system. Okay, now this scaling function here was phenomenologically obtained in the previous paper. However, here it was also theoretically verified in these red papers here. So it is correct, let's say. So we will use all these ideas, let's say, to analyze our network model and to try to find both the scaling function, but also the scaling parameter of our model. Indeed, we already made some previous work on this kind of systems, and we introduced in these papers the Hermitian diluted banded random matrix, because if now we will talk about networks, and as I presented to you the adjacency matrix of the networks we are interested in. So what I didn't say is that inside this band, inside these matrices, we have lots of zeros. So this is not a full random matrix. This is a full this is a diluted adjacency matrix, which will correspond to a diluted random matrix. So we then introduced the diluted version of the Hermitian banded random matrix model and performed a similar scaling as the one I presented to you before. And what we found is that, again, the parameter beta, which is the scale localization length, scales as a function which is not so complicated, but we have to add this power here. However, this quantity x, which is the scaling parameter of the model, now includes also sparsity inside the band. So in the following, I will already start with the model we are interested in this presentation here, which is the non-Hermitian diluted band random matrix model that I will define in the following way. So we will consider n times n real non-symmetric matrices. We will put random numbers inside the bandwidth B of this ensemble of random matrices, but then we will also define sparsity inside the band, meaning that a fraction of the elements inside the band will be 0. So the idea is that this sparsity will be, which is kind of probability of having ones inside the elements difference from 0 inside the bandwidth. If this sparsity, this parameter here, takes the value of 0, then we have a matrix which is null, a null matrix. But if we have this parameter alpha equal to 1 and b equals n, then we recover the Ginevre ensemble, the real Ginevre ensemble. That's the idea here. This is how is defined this model. So we will do something similar to what I showed to you before in the paper of the original proposal of band random matrices. So we will work with this scale localization length, which now we define as the average entropy of the eigenvectors of this random matrix model, normalized to the entropy of the real Ginevra ensemble, which is the reference model here. And we will define now this ratio here, this ratio x, which is what we call the effective band squared divided by n. Now the effective band, we define it as a number of non-zero elements per matrix row in this model here. And when we plot this beta as a function of x for different values of alpha, for different dilution of the band, so we have these curves which look very similar to the curves of the original paper. However, they are displaced by this parameter alpha, for this dilution parameter. Now, the goal is, or the goal will be, to try to find a new scaling function which absorbs or incorporates this parameter alpha, such that all these points fall one on top of the other, on the same curve. In that way, we will scale, let's say, the quantity beta. So we realize then that this scaling function of the original band random matrix model is equivalent to this one if we just make some very easy algebra. So we will plot, instead of beta versus x, we will plot beta over 1 minus beta versus x in a log-log plot. And this is what we get. Now, what we observe here is that in a very wide range of parameters, these curves are straight lines in this log-log plot. So that means that there is a power law behavior of this data here. So we will fit, or we fit this linear trend of the data by proposing this scaling law that we will define as x star. This will be our new scaling parameter that now depends on alpha, on the sparsity. And when we plot, again, the data as a function of x asterisk, the new scaling parameter, then we see the collapse of almost all the curves for a wide range of parameters. If we go back to the original figure, then we observe indeed the collapse of all the curves. And now we have already defined a scaling function here. So we found then that our parameter beta, our variable beta, the quantity we are looking at, so scales as this x star, where this scaling variable is now a function which is a non-trivial function of the parameters of the model, which are 3: alpha, which is the sparsity, b, which is the bandwidth, and n, which is the size of the matrices. And now all the data falls one on top of the other. Now, but this is for the non-Hermitian diluted band random matrix model. However, we still have to work on these ideas, but on the adjacency matrix, on the original adjacency matrices, which are not exactly this model, because they are some additional structure. There are block structure and also the structure for the multiplex, which is different. So we will define then two now ensembles, which are more closely to the adjacency matrices we started with. So we will consider now let's say multi-layer network, directed multi-layer network. We will consider we will introduce the sparsity alpha as a characteristic of these non-zero elements inside the effective band. This network will consist of m layers of size L. So the total size of the matrix is n again, but the parameters of the model are alpha, m, and L in this case. Again, so we look at the scale localization length. We redefine the ratio B effective square over n, because now the B effective is a bit different because it depends on the parameters of the model. we observe a similar behavior as a function of the sparsity, and we perform a similar scaling in order to get all the curves collapse at the very end. So we find again a very good scaling, which has exactly this form, which is also very simple. However, the new scaling parameter now depends on the original parameters of the model, which is, as I said, M, which is the number of layers in the multi-layer, L, which is the size of the layers, that in this case we are considering all of them to be the same. However, we can also play with this parameter here, and alpha, which is the effective sparsity inside the layers. And this is for the multi-layer setup. However, we can also, moreover, we can also look at the multiplex setup, which is here. We again define the corresponding random matrix ensemble, which is characterized by again by the number of layers, which has m layers of size L and sparsity alpha inside the layers. So we perform a similar scaling and again found a very good scaling with a new scaling parameter X, which now depends on the 3 parameters of the model, specific model. So we can conclude now, so because this is all I want to show to you. So what we obtained here is that we found that the normalized localization length beta of the eigenfunctions of this model, which is the non-Hermitian diluted band random matrix model, but also of directed multilayer networks, the adjacency matrix of multilayer networks, directed multilayer networks, and directed multiplex networks, scales all of them as this quite simple function, where of course the parameter x depends on the parameters of each of the ensembles we're defining here. In particular, it depends on the effective bandwidth of these three specific models. Also, this parameter x scales other measures that we also computed, like the inverse participation ratios of the eigenfunctions, the ratios between, concerning the spectral properties, the ratios between nearest and next to nearest neighbors in the complex of the complex eigenvalues, because these matrices are non-Hermitian, so they have complex eigenvalues. And also, it scales the ratio between consecutive singular value spacing, which is another quantity we use nowadays as a random matrix tool to characterize, in particular, non-Hermitian random matrices. Also, this scaling can be written in a quite interesting form, which is this one, which has also an interesting meaning, because it says that the inverse of the entropy, let's say, of the eigenvectors can be divided in 2 contributions. One which comes from the let's say one which is size dependent, and the other which is non-size dependent, depends only on the sparsity, let's say, on the properties of the network, let's say, in this case here. And all these results, or part of these results, are already reported here in this paper in the archive. So if you want to see some more details, so you can go to the posters of Marisol and Gabriela, and also you can look at this preprint here. Thank you very much.
Okay, so thank you very much for the talk. Are there any questions? Yeah, Jack.
Yes.
Sorry, when you have an adjacency matrix,
yeah,
you always have ones. The coupling is 1. It is always positive.
No. In this case, we are using weighted adjacency matrices. I didn't say it carefully, yeah, but we are using randomly weighted adjacency matrices.
Okay, so then my question is, what is the difference between choosing it all 1 and with your weighted case? What is the effect of the weights?
Yeah, it's not a big difference by using weights. The main difference is that we cannot explore the complete, let's say, a range of parameters, because in the case of a non-weighted adjacency matrix, if we consider, for example, a full or a complete graph, that will be a matrix full of ones. So that's not that's already out of the RMT, let's say, scenario. And also, if we have a very diluted matrix where just some small, just a couple of entries, so we get a matrix which has lots of degeneracies, and also it's not, let's say, a matrix which is handleable, let's say, in the RMT sense. So with weights, so we assure that we can go to both limits, to the full network scenario and the isolated network scenario.
The weights can be both positive and negative?
Yes.
Okay.
Yes, can be.
Other questions? Yeah.
Just to be sure, so
Yes.
alpha was the parameter to talk about sparsity, right?
Yes.
So it's between 0 and 1 is the
Yes.
probability.
Yeah.
And the delta is a new parameter that appeared, which depends on the sparsity, right?
Yes.
But it's not alpha.
No, it's not alpha. Yeah,
And this
depends on
delta,
alpha, but this depends smoothly on alpha, or very small on alpha. This delta and gamma are parameters which are of the order of 1 always.
Also, okay.
Yeah.
Thanks.
I have another question. I mean, so in terms of the sparsity parameter alpha,
Yes.
so you mentioned that alpha goes to one limit for the band matrices. You
Yes.
have this Geneva ensemble, right?
Ginebra, if the band also goes to the
Full
full matrix. Yes. Yes.
So what happens to the eigenvalue density as a function of this alpha or B or whatever? I mean, if I just look at the two-dimensional complex eigenvalues. So average density, for example, in the Geneva case, will just have a circle, right?
Yes.
So
In this case also.
in this case also, it doesn't
Yes,
depend
yes.
on the alpha. I mean, it doesn't become anisotropic or something.
No,
I see.
the circle is not deformed. It's just more sparse also.
I see.
Yes.
I see. Okay.
Yes.
And why is this parameter, b square over n? Why is it b square and not b cube or something? I mean, is there any simple argument for b square over n?
Yeah, that's well, to be honest, I don't recall the phenomenological, the
Right.
physical interpretation of
Right.
the ratio,
Okay.
but it's explained in the paper
Yeah.
by our
Okay.
colleagues Israelev and co-workers. Yeah, sorry for that.
No, that's fine.
Yeah.
Okay, so other questions, comments?
Concerning the eigenvalue density, since the matrices are always real, I suppose, we have real eigenvalues, exactly real eigenvalues,
No,
in
in
a
this
somewhat
case-
singular extent.
In this case, we have a non-Hermitian matrix.
Yeah, but values come in pairs,
Yeah.
right? In
Yes.
complex conjugate
Yes,
pairs.
yes.
And then, of course, there is a finite probability that they come actually both on the real axis.
Yeah.
And so there is this straight line which has a singular behavior. Do you see that in your simulations? And is it important or not?
We haven't looked at it, to be honest.
Okay.
Okay, so if there are no other questions, let's thank the speaker again.
Thank you.
Okay, so for the next talk is online, I suppose, right? So can you put the... Yeah.
That's it.
Rafael, can you hear us?
Yes, I am here. but
Okay.
I cannot see anything but my screen.
Screen.
You see my pointer.
Yeah, I mean, we can see your screen and we can see you, but I don't know, he says that he cannot see the audience. Is that okay? Okay.
here, so I have another screen. So,
Okay. No, that's fine then. I mean, you have to just give your talk and we listen to you. Okay, so our next speaker is Rafael Barrio from the Institut de Física UNAM, and he's going to talk about your title, Rafael. So, yeah. Please, anyway, you can start the talk. You have 40 minutes.
That's the title.
Okay, modeling the creation of friends and foes in groups in small real social networks. Okay. Thank you. Okay, Rafael, go ahead, please.
Yes. Well, thank you for the invitation. I'm very sorry I couldn't attend in person because of health and other issues that I got up here. But let's try to accomplish something. So this is a meeting on complex systems and stochastic processes, and what I'm going to talk about, it has to do a lot with complex systems, very complex systems, which are social systems, social networks, and stochastic processes inherently associated with social interactions. So this talk has the same title as the last paper we have published with my PhD student this year. My PhD student is Alberto Garcia, and here is Sidney Golesensky, who is my collaborator for so many years, and here is my former PhD student, Gerardo Garcia Naumes, who now is a big professor at UNAM, and we gathered together to produce this work. But I'm not just going to concentrate on this work, but because I can see that I could talk about many, many interesting things about social networks. So we will start by defining a social network. Well, for that, we need some fundamental properties that are shared by all social networks. First of all, they are a small world. That means that with very few steps in the connections in the network, you could reach a large number of people. The second, that they are weighted. So the adjacency matrix is a weighted matrix because the interactions will vary in intensity. Third, they are sparse. And this, I put Dunbar, who is one of our collaborators. You know about the Dunbar number, that your brain cannot process friendships or relations with more than 150 people. And this is a fact. And this is seen in all social networks. And the other thing is that the structure of a network is based on communities. That means there are clusters of nodes connected very intensely between them and weakly connected with other communities. So, just to give you examples, I have taken from the internet these networks. This is the networks of random Griffin strands, and shows all the characteristics that we were talking about here. There's another social network here, which is a network of TV actors. And you can see also these clusters and weakly connected clusters. And here I have a very interesting picture of a network of diseases. Yeah, human diseases. As you can see, that the structure of this network is very similar to a social network. So the question remains if diseases are also social interactions, and which was in the big discussion in recent years due to the pandemic. Yeah. Now, you could study social networks from big data, like usually the internet or the mobile phone calls in certain network, but these are not really social networks. These are, I mean, just they don't fulfill this requirement that you don't have many interactions. with other people. And what is called social media, or social networks, like Instagram, Facebook, and Twitter, and all that, are not really social networks. And then the first question was, what is the connection between these kind of networks and real social interactions? And the master thesis of my student actually tackled that problem, which actually is very interesting because he had data from about 7 million people in Twitter, and he filtered the data to the case of Mexicans that were talking about the COVID-19 policies in Mexico. And there was a debate. So this is very closely related with what our friend before was talking about, this polarization problem. Because the first thing that you find by analyzing the data is that you find the society divided in roughly two clusters of equal sizes. One is the anti-government and the other is the pro-government cluster. And all the other communities are sort of diluted around here. And there is another interesting cluster, which is the news, which is mostly connected to the pro-government, very suspiciously, right? So when you do a principal access component of the data, then you separate the clusters very well, and then you can study them separately. And there are basically two clusters of the same size, and then there is a small cluster of people who talk only about COVID, about the disease, without reference to the politics. Yeah. So this is very interesting. How do you extract real social interactions from that? So we did an experiment, which is we calculated the susceptibility of the network, which is defined by this thing, where S is the size of the cluster and NS is the number of clusters with that size, and we exclude the larger cluster. And then we start diluting the network by eliminating the interactions, the pair interactions, starting from the strongest interaction. This is all normalized, and then going destructing the network. And as you can see, if you look at the number of co-tweets or co-hashtags, then they diminish very smoothly, as you could expect. Nothing happens. Yeah. But if you do it the other way around, that means that you start eliminating the weak links before, then you very soon have this peak in the susceptibility, meaning that there is a phase change in the system, a phase transition. And this phase transition means that the network that was fully connected before becomes a series of disconnected networks that they don't talk to each other. And if you examine these disconnected networks, actually belong to families or groups of friends and all that. So that's the way we find the real social communities in this network. Okay, so what I'm going to talk about is based on a paper that we published a long time ago, proposing a dynamics, how people form an opinion. You have heard about the voter model and the Axelrod model and all those things, which are all sort of spin models, quantum spins, Ising model or whatever. And the idea was trying to get rid of that. So we ended up with a dynamical equation that we call it coevolution, because two important things happen in a network. First is the dynamics of the state variables Yeah, in this case, the state variable is a single state variable, which means the opinion. And it's a classical spin. It's not a quantum spin, so it could be 1, -1, or anything in between. It's a continuous variable. It assumes that there's a specific dynamics, a kinematics here for this sort of interactions. And then there should be another part, which is an operator that acts on the adjacency matrix and changes the connections. So makes sort of a rewiring according to the values of the state variables, the time, and also this G, which is a parameter that measures when you're going to act on that, how many time steps you need to act with this operator. So this actually combines the two things that we were listening to in the former talks. And so, yes, there are internal and external factors that dominate in the dynamics of the opinion formation. One is a sort of a long-range interaction, which is here. So you sum over all the people that are in the network, and then with a function that diminishes with the distance, yeah, because you are less influenced by people who are remotely connected to you. And this is an important thing, which is a randomness in here. This is a random parameter that we call the attitude parameter, because not all people react the same way facing the opinion of the crowd. Yeah, there are people who follow the crowd, the ship, and there are other people who go always against the crowd. Yeah. So this parameter also goes from 1 to -1 in a continuous way, in a random way. And then there's a short-range interaction, which is just a pair interaction. And this actually, what it means that when the two people have the same sign of the state variables, either positive or negative, the slope is positive. So they are reinforced in their conviction, either positive or negative. And if they are contrary, it becomes a minus, and then that means that they are less convinced of their opinion. And this factor here is a sort of external field that actually favor one or the other, the 1 or the -1. We haven't used that very much, but yeah. Oh, sorry. What else? Oh, I think I have explained everything. If you have questions, sorry, because I don't see. This is so old that I tend to think that there are people who have never seen it before. Okay. So the macrodynamics means how this operator acts to rearrange the network. Well, cutting bonds is quite easy because you could say that the probability of cutting a bond ij is just is proportional to the difference in opinion. Yeah, if they think in opposite ways, so there's no point of interacting anymore. But adding up bonds is more difficult. And according to the psychologists, there are two ways of adding bonds. One is called trial treasure, and probably this is due to the English people, because English people cannot meet new friends if they are not introduced before by a third person. So that means that this is triangular, this triad interaction between the people. And of course, you choose the ones which share your opinion at this sign. The other mechanism to do that, to meet new friends, is called focal closure, which some people call homophily. That means that they have the same attributes. For instance, you play tennis. What you do, you go to a tennis club and you find there people who also play tennis. And who you play with, oh, well, you choose the one who plays at the same level. No, not to be boring. So this is actually what you do here. And of course, you have these two rewiring system processes, then you could make a proportion of if you use the Q or you use the R to rewire the network. So the results are very funny and they are very nice. So I have plotted several single node properties of the network, like the degree, the clustering coefficient, the susceptibility, and the length, average length, etc., the second moment, everything. So we have plotted here, and everything goes smoothly, except the susceptibility. Yeah, and I've plotted here as a function of this parameter G, which measures how often you rewire the network. Yeah, if you rewire very often, so G is small, then what you get is what you expect. If you start with a random network, you end up with two clusters that don't talk to each other and roughly of the different size. And this reflects these polarization things that we were talking about before. So on the other hand, if you don't rewire ever, then you end up with a random matrix that you started with. But in between, here in this region where the susceptibility increases, then you have communities. And I think this result is very relevant to societies. Yeah. So societies change links, change acquaintances in different time scales. Yeah. So you could examine, and you could see the paper, and we examined this in a mean field scenario because we treat them like classical spins, yeah, and then we actually found a Brillouin curve, a Brillouin law for the magnetization of the system. Yeah. So now in this work, what we did was some experiments in classrooms. Yeah, we chose several classrooms in Mexico, and they are small groups from 9 to 30 people, though different ages, from 10 to 40. And we asked them to designate 5 friends and 5 foes, right? Obviously in secret. And then we collected the data. And then in Hungary, there are also classrooms, which are larger groups, more than 30. Ages are from 9 to 15. And we label, and we asked them to label their mates from -2 to 1, -2, -1, 0, 1 or 2, depending if they consider them enemies, which are negative, or friends, which best friends are 2s, are positives. Yeah, and so we collected the data. Now, the results for the Mexican data analysis are here. In a sort of very specific way, we calculate the accumulated probability of being mentioned against the number of mentions. Yeah, and as you can see, the friends and foes are different curves. It also depends on the age. So as you grow up, this actually gets steeper. So that means that you get more assured and who you mention. Also, the curve for friends starts from 0, meaning that there are some people with zero mentions, yeah, but the plot for enemies is different. So there are not people with, there are some people with zero mentions. It's the other way around. Okay. In here, everybody's mentioned sometimes, and in here there are people who are never mentioned. Yeah, and it increases as your age increases. So it means that you will become more discreet and more thoughtful about who is your enemy. Okay. So now we have to model this, and the model has two parts. One is to model the dynamics of the network, and the other is to model the action of voting for somebody or naming somebody. And the model was taken from this paper that we published a long time ago with Robin Dunbar, which caused a great commotion when we published it, because, well, you see, we can see that we were mentioned immediately by various media, MIT Technology Review, Science News, BBC, the CBS, etc. There were many articles commenting this thing because they said, the scientists said that lies were good for society, which is actually not true. What we said, that there is no possibility of having a social network without lies. That is true. Yeah, we also have some various articles commenting this paper. So, but I mean, all the fuss is nothing. We have seen the former model of opinion formation with one variable. What we did was extend this model to two variables. One that is your true opinion, and the other is what the opinion that the public, the others, think that you have. No? And if these two variables are the same, then you are completely honest, yeah? And if these variables are total, if they are opposite, then you keep your opinion private. So partially honest, or completely honest, etc. So, well, we applied this model to this case. We have also two variables, your private opinion and your public opinion. And you also have this short range and this long range interaction with the attitude parameter. The definitions are roughly the same, except the linear function in the case is linear with the distance. But now, obviously, the direct interaction has to do with the public variable, because nobody knows what you think, but you know exactly what the others want you to know. Yeah, I don't know if I'm getting a bit cumbersome, but I mean, I just explained that before. Yeah, this short range interaction to the number of neighbors that you have, and you use this variable, which is composed of partly private and partly public, and then the public thing is made by summing up over all your neighbors the public opinion. I don't know if that is clear. So this is the dynamics. There is no rewiring in the system because the experiments are made in classrooms in which rewiring is not, there's not enough time for rewiring. So the problem is quite easy now. But now, the dynamics of the link weights, yeah, we assume that they grow linearly. If T is positive, it grows, and if T is negative, it diminishes. So the positive bit has to do with the values of the state parameters, which are the two, the x's and the y's, in a certain proportion. And you mean that if all of them are the same, this is positive, very well. But if they are all opposite, because of this -1, it becomes negative. And we interpret that the positive links means that you're reinforcing your relation, so there are friendly relations, and the enemies have negative links. They become negative. Yeah. So an example of this numerical calculation, this is the adjacency matrix elements as a function of time. Some are negative, some are positive, and some change between negative and positive, because this is a complex thing. And the end result is that you have clusters, the ones whose opinion is generally 1, and the ones whose opinion is generally -1. And there are some indecisive people here in between, and that they form the link between these two clusters. Now, the second part of the model has to do with the way that you choose your friends and foes. Okay, so let me define a fitting function which takes into account all the node properties of the network for each one. Yeah, for each of the agents, we calculate the betweenness, which actually measures the connectivity that you've got between one side or the other of the cluster. So how many trajectories go through you. Then the clustering coefficient, which means how friends of friends you have. So means the number of triads. Then obviously the degree, which is the number of neighbors, and also the weights of the adjacency matrix normalized to 1. So you divide that by 4. You take all these properties of the network in equal footing. Yeah, and so we calculate this difference of the function between agent A and agent I, and we say this is homophily. The ones with the smaller delta are friends, and the ones with larger delta are foes. Yeah. And yeah, this works very well for friends, but not for foes. That's the first difficulty that we get. So we want to match the data, the experimental data, by only using this fitting function is quite difficult. Now, this result tells us that friends are chosen differently than enemies, which is obvious probably for many of you. Then the only thing that we say, okay, we say that your worst enemies are the ones who have the lowest value of the element in the adjacency matrix. So the model is applied like this. In Mexico, they have to designate 5 mates. So friends are the 5 links with the smallest delta. The enemies are the most negative values of the adjacency matrix, provided that you've got at least 5, because there are people who do not mention 5. Yeah, the average of mention is 4, really, meaning that they find it very difficult to signal people as enemy. Okay. Yeah, if you don't find 5, then you will complete with this larger delta. Okay, in Hungary, the thing is a bit more cumbersome because freedom means randomness, really. When you are free to choose, then randomness appears. Yeah. And then we define 2 threshold parameters, beta 1 and beta 2, for friends and foes. So beta 1 is associated with this delta, and beta 2 is associated with this adjacency matrix. Yeah. And then we average over many simulations to take all this randomness into account, and we adjust the percentage of the distribution for friends and foes. Maybe it turns out to be 12 and 40 for friends, 12 for friends, and 40 for foes. And then the values of beta are taken as random values with a dispersion of from -5 to 0.5. So if we do that, we end up, I don't know, I think I did something very wrong. Let me, yeah. I think I missed one of the slides. Okay, so the results. These are networks taken from the data in Mexico. This is the complete network. This is the friendship network, and this is the enemies network. You can see there are differences between these two networks in the structure. The friendship has this clustering, these communities structure, while the enemies network doesn't seem to show that, and also is quite sparse. So if we make the simulation, we take a given realization, we get these results. And you can see they compare fairly well in the sense that the enemies show this clustering, these communities, while then the enemies don't. Yeah. In the case of Hungary, the networks look quite different. Yeah. Still, the friendship networks is form of communities, close gangs of people, while the enemies is very sparse and not connected. And in the calculation, you find something very similar. Yeah. Now, a more quantitative comparison between the model and the experiment is by calculating these cumulative probabilities for the cases of the Mexican and the Hungarian experiments, which look quite different. Actually, that was the purpose of choosing Mexico and Hungary, because we are very different people. And as you can see, the comparison between the simulation and the data is quite nice. It's quite good. So, particularly this fact that foes actually do not start at the origin, yeah, but friends nearly start. They always start at the origin, and also then this probability goes up for foes in both cases, but not in the same way. Yeah. Okay. Now this is just to show that if we take in the simulation the same method as for the Hungarian experiment, this method of the random parameters beta that I show you, the agreement is much better. Okay. The conclusions. Well, there are many conclusions. I mean, because we talk about society, we don't know how to speculate what this means in a real society. But I mean, since we're taking an experiment with a real social network, then we could say something. Yeah. According to our results, the criteria for selecting friends and enemies are very different, and they depend on different criteria, so to speak, on different processes. While a friendship, you have to nurture, you have to cultivate people on time. with enemies, you don't have to do that. I mean, you just say, okay, this is my enemy, period, because of one action or something like that. The model reproduces the structure of the models, which is very nice. And the other is that people are reluctant to make their enemies public. And then there is a question of the appearance of the public enemies number one. We found that in the Mexican society, there is always a public enemy number one. That means that practically everybody names that person as an enemy. While in Hungary, that is not true. And we are speculating that if this appearance of the public enemy number one has to do with bullying, which is a very, very serious problem in schools. So we also found that popular people with many links, also have positive and negative connections in similar numbers. That is, we have in Spanish this say that said, no soy monedita de oro para caerle bien a todos. Yeah, I'm not a gold coin to please everybody. So that means that it's quite impossible to please everybody. And probably that might be the birth of these polarization things that we are seeing in our society now. Especially in these times where social interactions, real social interactions, are being substituted by the social media and the internet. Okay, that is actually, well, I went very fast. Yeah.
Okay. Okay, so thank you, Rafael, for the talk. Are there questions?
Hi, Rafael. Thank you for your talk. My question is, when you mentioned that the model works pretty well with friends, but not that well with foes, that is related with the conclusion where the people is open to say who is my friends, but not that open to say who is my enemy, because probably when I say somebody is my friend, is most likely he say I'm her friend, but I can say somebody is my friend, but in real I consider it like my enemy, but I don't reveal the information to people.
Yes, because you fear the consequences, probably. Yeah. Yeah, that is quite natural thing. Yeah, the other thing is that the disappearance of the individual who is considered the public enemy number one, it actually is reflected in politics as well, right? And that there's some individual that everybody thinks he is a bad person, and you cannot hide that. But there is not such a phenomenon with a public friend number one. Yeah. There is not a single person which is considered a friend by everybody. So that is a confrontational society that we're looking at the moment, probably. If you translate this to politics, probably this model could be applied, as we applied it for the COVID Twitter thing, that we could see immediately this polarization phenomenon, and we found a lot of hypocritical people as well. So this fact of hiding your own opinion is quite important. We have to make the analysis of the model, how it behaves when we increase this parameter of the proportion between privacy and and not privacy, to see how it behaves. Because I think that if you are totally honest, then immediately there are polarizations. But if you hide things and you try to deceive other people, then uh, uh, that doesn't occur. And that goes in accordance to our former paper about lies. Yeah, because when you lie to people, lies actually form a sort of a glue that maintains society together. Because you cannot be totally honest and tell your wife, look, yesterday I slept with someone else. You cannot say that because that will be complete destruction of the society. So you have to lie sometimes. But the amount of lies, well, in that paper about lies, we say that white lies and the other lies, I mean, pro-social lies and anti-social lies, the lies that you usually use in your daily interactions is about 25%. That means that 25% of the statements that you make with people are actually lies. Lies in the sense that you're not being totally honest. Yeah, you're not saying exactly what you think. And I think that's why we apply that sort of idea to this experiment. Because, I mean, people have studied networks of friendships very extensively, but not networks of enemies. And what we found that in certain cases, the enemies form also networks which are really tied together. It's only one small cluster, and we call them the fundamentalists, call them, right? And they're against everybody else, yeah? And that is actually seen in our society, this terrorist association and these organized crime associations and all that. So I think this kind of studies, although very sort of simple, as a physicist is always thinking in simple things, they are quite relevant to understand some of the social processes that are impacting our lives nowadays. Thank you.
Okay, are there any other question? Okay, so if not, let's thank the speaker again, Rafael. So that's the end of this session, and we go for lunch and come back at 2:20. Is that right?
Hi everyone. We are going to take the group photo for this Congress. So if we can go out to take the photo, please. Unos segundos, se prende. Sí, por favor.
¿Estamos listos? Muy bien, estamos listos para empezar la sesión de la tarde. La primera plática la dará Leonardo Dagdug de la UAM Iztapalapa. El título de la plática es Diffusion Under Confinement, A Journey Through Counterintuition. Adelante.
Okay, well, I want to start just thanking the organizers to having me here. It's a really nice pleasure. You know, I spent the vacations during when I was a kid around this place. It's in a very small town. Well, my grandmother from my mother's side was from close to here, in a very beautiful place with a very strange name. The name is Jalostotitlan. So it's quite big and strange. For short, Jalos, the people here just call Jalos. And so for me, it's very nice to be here. Well, I'm going to talk about the diffusion under confinement. The title just is the title of a book that was recently released. I'm going to give a very general talk about this topic. So anytime you want to know about any details, just please let me know. I'm going to be glad to stop and explain if you need anything. So this, well, the talk is going to be related with diffusion when the particles are geometrically confined in a tube or a channel, and we are going to try to explore what is the consequences or to have this diffusion in a channel or a tube. These channels or tubes should be kind of, they are not wide and they are very long. So let me just start with this talk. Okay, well, the motivation is, you know, there is a diffusion everywhere. It's ubiquitous. You can find it in biology, in chemistry, and physics. I mean, everywhere. But there are some things that, well, for me, it's like I'm amused that the people can do this kind of things. And I mean, I can spend talking an hour about the examples about diffusion confining in geometries. I mean, I'm going to talk about just a very nice example. This from a team in UK. These kind of things are made by Stefano Pagliara and Ulrich Kaiser. It's amazing what they did. I mean, well, of course they can put particles in channels, and they have this kind of membranes. They can measure the mean square displacement. In fact, they can, well, as everybody knows here from the very beautiful talk yesterday and the day before, that now the experimentalists can have these traps, this laser twist. But these guys also can make channels with a DNA origami. So they can do whatever they want. It's kind of amazing. I mean, if you ask to do the channel as a shape of a Coca-Cola bottle, they can do it, and they can put it in a membrane. So it's quite amazing. They put it in a membrane. They can measure how these particles cross, so they can do anything. And then when they have these DNA origami channels, they can absolutely put these optical twisters there, and they can do a lot of things there. It's quite amazing. And of course, when you confine in a geometry particles and they are Brownian particles, I mean, it strongly depends on the tortuosity and the shape of the channels, on the how many channels do you have. So it's a kind of interesting problem, and a lot of people face it all the time. So, okay. Well, mostly all the people here is very, I mean, the people know about the history on diffusion. I just probably, well, this Brownian motion is really what Robert Brown seems to watch in a microscope. Robert Brown was better known, but because he was a biologist, he was the guy who first said that the cells of vegetables, I mean plants, have a nucleus. So it's very famous in biology. And of course, we know that he was really the first guy who studied this and tried to make it, you know, in a very good note. And he published a very nice paper about Brownian motion. And then, well, everybody knows about Adolf Fick. I'm going to go back later, I mean, forward then. But well, I'm going to show you something later, but the equation that we use is the Fick equation for follow the concentration of those particles in position and time. Then Smoluchowski did a very great job. Even he published in 1906 the work, well, the first work made by Smoluchowski was finished in 1904. And he was devoted more on kinetic theory. He used all the Boltzmann ideas, and he get the relation between diffusion and viscosity. And then, well, everybody knows the excellent work by Einstein with, I mean, he introduced this stochastic part of the processes, as well as Paul Langevin. In fact, Smoluchowski in 1916 made a also very big step with the Smoluchowski equation when he introduced an external force to the Fick equation. And then, well, Jean Perrin, who made the experiments. But there is always a surprise. And recently, well, recently, not so recently, but probably 10, 15 years ago, the Australian Physical Society pushed very hard with two really nice articles, in fact. I mean, they tried to the people to know about these articles. The articles were written by William Sutherland, and they were published in 1904. These two papers shows the relation between the viscosity and the diffusion coefficient. Was the first guy who did it, really. And the two papers appears one in a conference, I mean, in proceedings of a conference meeting from the Australian Physical Society. So, I mean, it was a proceeding. Nobody read it. And the huge article appears in the Journal of the Physical Australian Society, so nobody knows about it. Well, it's what the people thought, but let me tell you something. In correspondences between Einstein and Michael Besso in 1903, Michael Besso told Einstein about the William Sutherland works. So Einstein knew in 1903 about the results getting by Sutherland. So, I mean, I don't want to say anything more than a lot of people was working on that. And I mean, all these stories appears mostly at the same time in very different places in the world. So, I mean, William Sutherland, it seems that was really the first one. Okay, so, I mean, I don't have to say too much about diffusion here. I'm just going to focus on if we plot the mean square displacement on a free Brownian particle on time, we have this beautiful straight line. And the important thing here is that let's see what's happening when you put a particle in a channel. So it's this channel is made by it's a sinusoidal channel. It's quite simple, and what I'm going to show you It's a Brownian dynamic simulation of, I mean, I'm going to show you just one trajectory of these Brownian particles. But of course, for these lines, I did it with 25,000 random walkers. And if I can remember, the time step was 10 to the minus 6. So you have to do 1 million of steps to get a unit of time. So if the particle starts in a channel, I mean, no, particles start to just given a diffusion in a channel. At the beginning, they really don't know that they are in a channel. And if you measure the mean square displacement at the very beginning, you get a straight line, as in a free diffusion. I call the diffusivity of the diffusion of constant diffusion D naught. And if you continue in a free space, you get this line. So what's going on if you start with the, I mean, with the evolution on time? Well, particles start feeling that they have something, some barriers that, they cannot cross, and they start to see that they cannot move as easy as they could in a free space. So this is a transient behavior here. And the mean square displacement goes to the t to the power of, in this case, I put alpha. And then, if you continue with this, particles really knows that they are in a channel. And you reach this effective diffusion constant or diffusivity. So, I mean, you have to wait a lot. You have to be patient, but you are going to reach it. And again, you got this t to the power of 1. So it's again, one of the main problems is to find in this field is to find this the effective diffusion. In this talk, I'm going to focus on how to handle to find this effective diffusivity. And we can measure alpha in different ways. And alpha, of course, at the very beginning goes from 1 here for a free particles, then goes down, then goes up, and again reach 1 here. And of course, this effective diffusivity should have some relation with D naught. So we try to find out how is this thing. So let me tell you a little bit about the projection method. So we cannot do a lot of things with with the Fick equation and the boundary. All the boundary condition of the system is kind of hard. So as a first approach, we try to project this problem in 1 dimension. So we start just, trying to get a projected 1-dimensional density. And we made it just taking the integral from one of the boundaries. We call A1 to A2 here. This is the width of the channel. And in fact, this yellow dotted line is the midline of the channel. And if you do this and you impose the boundary of non-flux in the walls, and we're just playing with these 2 variables here with the boundaries, and and imposing a very, it's a very zero approximation. What you say is that this P does not depend on Y, because this not is very narrow. These channels also have zero approximation. You say, well, this depends on X and T, and because I am doing the integral over dy, I have this one. I just have to do the A2 minus A1, and it's the relation that we have. We finish with this equation, which we call, what Swansik's call it the Fick-Jacobs equation. This equation is exactly the same as the Fick equation, very, very close. The difference is we have the width of the channel here and here. So if the width does not depend on the position, you can get this out, and you have just the Fick equation. Okay, it's the simple equation you can have. And Swansea is a very nice story. So Swansea published this paper in 1992, And let me tell you something. Swansea used to, at the end of the day, used to go to the library because his wife worked at the NIH, in the National Institute of Health Library. So at 5 o'clock, he used to go and pick her just to back home. And one day, he was walking in the library, found a book on the floor. And the book was Jacob's book. And he just grabbed it and take it home and start read it. So that's the reason, because why all this story start. But the English version of the Jacob's book was in 1967, but in German was in 1935. So nobody knows about this book in a lot of time. And let me tell you something more. So I'm sorry it's too small, but I think this is the page 60 something, and it's from the Jacob's book. And Swansea, what found in this page, is this equation. And it's the equation I just showed, the Fick-Jacobs equation. So Swansea immediately thinks, I can do better. I am going to try something, but nobody knows about this equation since from this book, and this equation apparently since 1935. But you know, sometimes you have different eyes to read articles. So after starting bolding in this field, I start reading again the original paper by Fick. And in the page 65, what I found is this equation. Is the very first equation of the Fick's paper, is the Fick-Jacobs equation. So Fick starts saying, you know, you have a channel with some width, they call Q this width. You have this equation, and he saw by the first time this equation in Fourier's work. So really, Fourier was the first one to introduce the confinement in the geometry on this paper. So it's and then of course they said, well, you know, if you have if you have just a straight channel, you just have or a free particle, you have the Fick equation. So it's kind of weird. So it's from 1855. And never nobody take care about this. Probably even Jacobs. So it's kind of weird. Anyway, so we have here the Fick equation, but it's something very, very, very funny. Anyway, so how start the story? Swansea tried to prove the Fick-Jacobs equation with this D naught in the differential equation. He compared with not this channel, with a different channel, but the first thing that you see is you have the Fick-Jacobs equations with D naughts. I'm going to show you again the equation just to. Okay, so it's this equation. So you have here really a D naught. It's just the bulk diffusivity. So if you compare with a channel, this is a straight channel, not so easy to make of. It's a sphere with a small holes in both sides. You connect all these spheres, and was really bad. So he tried to do it a little better. So Swansea, in a very complicated paper, this paper from 1992, he said, you know, let's try he arrived to this equation. Instead of D naught, you have an effective diffusivity which depends on the position. And he immediately recognized that this was a Smoluchowski equation with an entropic potential given by the logarithm of the width. And so he tried to find this D effective depending on the position. and he tried to do a little better. And I'm going to get some intuition about what is this D effective depending on the position. Suppose you really have a really one-dimensional channel. Okay, so you can see, I mean, you can have the mean square displacement, and you project on X, you have the projection on Y, you do a little simple algebra, you have here that this effective diffusivity is given by this. It's a factor, I mean, proportional to D naught, and goes like a 1 plus the shape of this channel is a prime here. You cannot see it, unfortunately, to the square. So it's like the prime of this of the shape of this channel. So probably you have something like this, and Swansig made this equation is for D effective is this D0, and here you have the derivative of the width, this prime here, also you cannot see it unfortunately, to the square. So Swansig tried to do better than Jacobs, but was not so good. So this work was the trigger of this field, but the people just forget about this work because it's not working really good until a couple of guys from the University of Barcelona, Miguel Rubí and David Reguera, they just proposed some how should be the effective, and they could do much better. They could. So that was kind of the trigger was the work by Swansig, and the boost really was the work by Miguel Rubí and David Reguera. And then Pavol Kalinai and Jerome Perkus published a really nice a couple of papers in 2005 and 2006. And what they tried to do is a very nice job. They said, well, you know, just suppose that the concentration do not depend on the direction of the channel is not so good. So let's try to do some expansion of the concentration. So a perturbation theory with a parameter lambda. This parameter lambda is the ratio between the diffusivity on X divided by diffusivity in Y. So if we have a really small channel, it seems that dy should be much bigger than dx. So this is this parameter lambda. They compare the difference between the diffusivities in both directions, and well, they try to do this theory. It's really nice. A lot of work, but really nice. So what they got is the Fick-Jacobs equation with a parameter here, and these parameters is well, they have this one because it's the zero order. Then they have the perturbation that goes with lambda, but they can invert it. And this is the effective diffusivity, is a great thing of this work. And well, they got the Fick-Jacobs equation, and for 2D, they have this effective diffusivity, goes like an arc tangent. And in 3D, they have something very close to Swansig, it's just the square root of the Swansig formula. And if you compare with the experiment, well, a lot of people work on this. I mean, people not just the team in Barcelona. A lot of people in Germany work on these problems. Peter Hange worked for more than 20 years in this. Luz Szymanski, Martens, Peter Tachner, a lot of people work there. Sokolov also worked in this at the beginning of this problem. But anyway, if we have now this perturbation theory, we can go, this is in the zero order, we recover the D naught, so we can do a little better probably. And in fact, they do. So the perturbation theory made by the Kalinai and Percus is quite good. And but you know, then all these works was made for straight channels and quite symmetric. And because you know, the Percus perturbation theory is not easy, nobody wants to go further than that. So, but sometimes you got a good student, you ask to work on this, and I asked a student for a PhD to try to see if we can find something for an asymmetric channel. Was to push in a little bit further, not too much, but push it. So what we got was this equation. Very similar to the Percus and Jevic equation, but now we have here the middle line of the channel. So here you can insert the asymmetry of the system, okay? So you, of course, obtain all the equations, a very general equation. You can obtain, this can be reduced to all the results known in this field. So at the end was, well, we tried to test in the community this formula. This is a work made by Ralph Metzler and his team. He tried to really push really hard with our equation. He put some parts that really is a straight channel, another parts where you have this asymmetry in one direction, this asymmetry in another direction. So he tried to push to see if this equation works, and it works. Here is they compare the theory, the diffusivity, the effective diffusivity from simulations and our theoretical result, and it seems that it's more or less under 10%, so was really good. But you know, the community stuck there for some time, and then when I saw that we can do this, then I start a new project, and I try to introduce the curvature and tortuosity of a channel. And it seems that was really a problem that you cannot go anywhere. In fact, everyone in the community told me that do not try to this. It's not going to be possible. But anyway, I tried, and the answer was extremely weird. I was trying to think how to solve this problem, for a long time. And once I was riding my bike in the Bethesda area in Maryland, US, and I was going from one lake to another lake. And I used to go around one lake, then go to another lake by a tunnel, and then go to another lake. When I was in my bike, I start to try to follow the middle line of the tunnel. When I follow the middle line of the tunnel, as is normal, you try to just go as good as you can do. Immediately I figure out that doing that, you always see a straight channel. So I say, well, this is the simplest channel we can handle. So the challenge now was how to reproduce this to explain, if I can put anything in a channel. So the idea is if you go to a moving frame just in the middle line of the channel, you are going to see a straight channel always. So the way I try to handle the problem is as follows. You introduce the Frenet-Serret moving frame in a middle line of your channel. It's something like this. If you have curvature and tortuosity, could be very complicated, but you can do it. It's not hard, not too hard. And now how to construct the channel, well, this is much more easy. So you have any shape you ask. I mean, you can choose any shape wherever you want, and all you have to do is, I mean, I have these very complicated curves. I mean, it's nothing. I mean, it's not so complicated really to describe it mathematically. So when you put all these together, you can construct your channel. So you go in the Frenet-Serret framework, you just see how you have around you, and you just move forward. At the end, oh, let me see, let me go back. Oh no, I think it's going to take a lot. Let's see. Oh, okay. So you can do it, of course, in 2 dimensions too. It's kind of easier. In 2 dimensions, you have your Frenet-Serret here. I mean, it goes in that direction. And now you can generate any channel. It's quite simple, and you always are going to see a straight channel. So now, what are the elements you need? Well, we have we need to construct the channel. And for that, we have to, I mean, to try to figure out new coordinates. So you have to, I mean, the way to construct the boundary of the channel is with tubular coordinates. All you need is kind of, you know, you just need to see this row, which is perpendicular to the Frenet-Serret triad here. You have just an angle, and you have to move forward. So you can parameterize this any curve, and the points inside the curve are given from the, I mean, to be inside of the boundary. There is not important really. The other thing is that you really need to write your equations in any coordinate systems. So we have to write the Fick equations, or the Fick-Jacobs equation. I mean, we start with the Fick equation, and you have to try to have an equation which can be invariant in any coordinate. So you have your flux here. I mean, don't take care too much about this. You have the flux, you have the you know, the concentration for in a very general coordinate systems, and you have the relation between the derivatives of the different coordinates, and this, at the end, you have this kind of diffusivity, bulk diffusivity, and I mean, the mathematics could be a little hard, but you can perform the reduction, and at the end, you can, I mean, at the end, you can do the reduction, you can obtain the generalized Fick-Jacobs equation, and so on. So what you have at the very end, I mean, you have this probably horrible equation, but you have an equation. And when you test your equation, this is the 0 order, and this is the first order. So it's kind of, we can solve the problem. Yes, we can solve the problem. And the reason is because everything you convert in a straight channel. Just, I know that I have no time. Of course, just to have fun, we have more complicated things, of course. And yeah, you say, is the end of the story? No, you can add a lot of things. You can put in here, you know, active Brownian particles. You can instead, in fact, you can put resetting inside your channel, and you start having fun. It's very interesting. I cannot go further because I don't have time, but you can do even resetting inside the channel. Thank you very much.
So we have time for some questions.
Thanks for the nice talk. I have a question regarding the presence of the channel walls. Well, when a particle is moving in a liquid, you have the effect, the hydrodynamic interactions. So is it easy to include them in this kind of descriptions, or?
Not really, but you can instead, I mean, to do all this theory, you just have a really perfectly reflecting boundaries, but you can put instead of harmonic, an harmonic one. I mean, it's you can put an harmonic potential inside the channel, and the only thing that appears is the temperature, but we can do it. Yeah.
Okay.
Thank you for a nice talk. So I have 3 comments.
Sure.
One is that, you know, you're focusing on continuous channels, and you know, back in the 80s, there was a lot of work on comb structures, and it was that, and for that, it was easy to estimate the diffusion coefficient.
Yep.
And I'm just curious, like, what relation, if any, is there with you know, your approach? And the second comment is actually in response to the person who just asked the question before, is that there's a huge field of hydrodynamic dispersion where you have a channel of some arbitrary shape, you have fluid flow, you have some kind of trapping on the edge of the channel, or like getting stuck in dead ends. And so there, the basic question is, what is the hydrodynamic dispersion coefficient? And there's the huge literature in that area.
Mm-hmm. Yeah. Yeah, well, I mean, we can also work with the comb shape of the channel, and we obtain the same result as the people has been obtained in the past. Yeah, but we can work on that. Absolutely. Yeah, thank you.
Other questions? I have a very brief question. At the very end, you said this was first order and the other was second order. In what?
Oh, I apply the procedure of Kalinayor and Perkus. So in the I have the whole theory, but I have to say something about the concentration, and I use a perturbation theory.
But what's
the zero order is when you just said that the concentration goes very fast in Y, immediately is equilibrated in one direction, and you just have another direction. The first order, you start to take deviation for this immediately equilibration in one direction.
Okay.
Mm-hmm.
Any other question? Oh, we thank Leonardo. Our next talk is asymmetric games on networks, mapping to Ising models and bounded rationality. It will be given online by Filippo Simaro. Are you there, Filippo?
Yes, can you hear me?
We can hear you, but we can't see.
Okay. Can you see my screen?
No. Yeah?
No.
There, now we can.
Now you see the screen.
No. Now we see you.
No, that's not good.
¿Sí? ¿Dónde?
Pero están configurando.
Okay. So they tell me we can see your screen. That's what he told me.
So you could see my screen now. Like if I do like this, see the start of the presentation.
There.
Okay.
Can you do it
right?
before you begin? Can you do it full screen?
Yes.
See? Let's do it. Yeah? Okay, you can start now. So.
Sorry, because I don't see it. Okay, anyways. Okay, it's all good now. So you see the first slide.
We see the title.
Okay, perfect. So thank you for having me here. I'm going to present my work on asymmetric games on networks, mapping to Ising model and bounded rationality. And the work was in collaboration with Serge Galam, who spoke this morning, and Marco Alberto Iavarone. I'm a PhD student of University of Pisa and University of Bologna in Italy. So just to define these games, basically, an agent can choose between two choices. For example, here, we can think of the two choices as two parties, one party in a countryside house and another one in an apartment in the downtown of a city. And to each agent is attached a fixed preference towards one or the other option. And for example, if the agent has a preference for the green option, so the house, if he reaches coordination with another neighboring agent, he will get a reward of 1. If he reaches coordination on the other option, so if he decides to go to the apartment, and also the interacting neighbor does, he will get a reward of less, and that's less than 1. If he doesn't reach any coordination, so if he decides to go, for example, if he decides for the green option and the neighbor agent decides for the red option, then he will get 0. So vice versa, here the preferred opinion is the red one. So if they agree in the green opinion, he will get S. If they agree in the red opinion, he will get 1, and so on. So the agent is posed on a social network. So we have this dynamics here, and his opinion, his choice is updated according to a logit rule. So basically, it's a stochastic update with exponential weight, and the total payoff, which is simply the sum of payoffs of all these interactions, is multiplied by a factor Ri, which is the attention to the payoff in the update, or else we call rationality of the agent. So we have a network of agents with opposite preferences with same intensity, and we are interested in determining the equilibria of the system, and which depend on the preference intensity, 1 minus S, the greater S, the lower the intensity, the social network of interactions, and the rationality parameters, which we assume to be homogeneous across the agent. So Ri is equal to R for every agent type. So the first result is that we can map this model, which was typically studied through numerical simulations, in this case of preferences of equal intensity but opposite sign. We can identify this model as a potential model, and we can map it to an Ising model. I do not really have time to go deep in the calculations, but we end up with a mapping, which is this. The Ising model is as an Hamiltonian with site-dependent magnetic field and a homogeneous ferromagnetic coupling J. And it evolves with Glauber dynamics with inverse temperature theta. So the mapping, basically, each magnetic field is a function of the preference intensity S and the degree of the node. And for the group A, which is the group that favors, for example, the green choice, sorry, the magnetic field is positive because S is less than 1, sorry. For the group B, this is negative, so it will have a negative sign. Beta is simply equal to the rationality, as one could expect, seeing the logit rule and the Glauber dynamics. So if we take into account for simplicity a k-regular graph and also a complete graph, so everyone is connected to any other agent, and we are in the regime of best response, so the rationality is infinite. Basically, the agent updates his choice to the one that maximizes his payoff. Then we end up with a random field Ising model at beta tending to infinity, so t equal to 0, which was the one studied by Serge in a paper in 1997. And basically, if we apply it to a k-regular graph, we have the same complete graph, but within the mean field approximation. And these are basically that there can be at maximum 3 fixed points. One is a consensus to the green opinion, a green choice, for example. So every agent chooses to go to the party at the countryside house. Or the second state is that every agent goes to the apartment. And the third state, there can be a third state in some regime, depending on the intensity of the preference, in which basically everyone chooses his preferred opinion. So the green agents will go to the countryside house, the red one will go to the apartment. So what we do more basically is we plot the vector field for these models, and we compare the vector field given by the mean field approximation with the real simulations, and we see that actually for finite k low enough, the basin of attraction of the real system is not really the one predicted by the mean field. Indeed, if we see the graph at the bottom left, this simulation, like the colored lines, are some trajectories for different initial conditions. This simulation doesn't really end up in the point everyone at his preferred opinion, but instead the consensus is a better attractor for that. So there is this discrepancy, and we just perform some simulation to see more or less what are these finite size effects. But actually our focus on the paper is to go beyond the best response regime and consider bounded rationality, which will scale here by a factor 1 over k, which is the degree of the k regular graph that we are considering. We are able, within the mean field approximation, to write the mean field equations and the mean field free energy, which I plot here, in the case of two equally sized groups. So half of the agents that prefer the green opinion, and half of the agents that prefer the red choice. So for low rationality, there is only one fixed point here, which corresponds to the state in which the total magnetization, which is a function of the average opinion of the group, is 0, until some point in which a transition, a ferromagnetic transition, similar to the Curie-Weiss one, occurs, in which two fixed points at almost at consensus pop up. And this is interesting, and it's tested with some simulations. So for the top line, I take a preference intensity of quite low, so high S. And in this case, basically, we have only one fixed point for all the three values of the rationality that I consider, up to r equal to 1. At r equal to 3, basically two fixed points pop up, and there is the transition. And these two fixed points are almost at consensus. Here, just to understand, the red line is the average opinion of the group that prefers the green opinion, let's say, or the red one, so to be more consistent. And the other one is for the group that prefers the other one. So these two fixed points almost at consensus appear, which does not happen in the bottom line, where the preference intensity is higher. We have that the fixed point is unique, and there is a huge distance between the average opinions of the two groups. We go beyond the mean field approximation with some further assumption for this type of ferromagnetic Ising model on specific graphs in this paper that we published with it's in submission, and it's done with people from Bologna. And the last thing that we are interested in is this distance between the average opinions of the two groups, which is a measure of polarization. So the higher is the distance, the more the system is polarized. So here I plot this polarization for different values of the rationality, so increasing the rationality from left to right. And we see that it varies according to the preference intensity. When the rationality is really low, it means that basically the update is random and we don't expect any polarization to occur. When we increase the rationality for all the preference intensities, the polarization increases monotonically. But for high preference intensity, so low S. It keeps increasing until its maximum. So basically, everyone is it has a preferred opinion, which is what happens in the best response regime. And while for low enough preference intensity, after having increased for a while, it starts decreasing again. It means that the system basically is interacting and they are reaching an almost consensus state if the preference is low enough. So by this, we can conclude with probably the main qualitative result of this model, which can be applied like for more realistic cases with some care. And basically, in these asymmetric games, by increasing rationality, which is intended as the attention to payoff maximization, and the payoff maximization is a result of coordination with the other agents, as well as the alignment to the preference. Increasing this rationality may lead the system or towards a very polarized state, or towards an almost consensus one. And this depends on the intensity of the preference. And this is something which is present in the psychological literature. It's observed. So I remarked that this work is with Serge Galam and Marco, that I thank, and it's published in Chaos, Solitons, and Fractals. And I wanted to say that I'm really sad not to be there, but Mexico was really, really too far away. And I would say gracias por la atención. Thank you.
So we have time for a few questions. Thank you very much for your nice talk. Questions? I have a question. What would happen if instead of having a constant rationality, you had a heterogeneous rationality, which I think is closer to reality? No?
This is, can you hear me?
Yeah.
Okay. Yeah, this is a more refined model. And we can think of like to start of assigning like a different rationality to the two groups. So one group is pays more attention to maximize the payoff, while the other does not, and see what happens like to start. But of course, in a realistic system, everyone has his own rationality. The assumption of homogeneity is rather crude.
Okay, thank you. Any other question? So we thank the speaker again, and I hope you stay with us for the next talk.
Okay.
So, the last talk is strengths of minority ties, the role of homophily and group composition in a weighted social network by Nicolás Carlock, José Nicolás Carlock. You have 10 minutes plus questions. Por favor, empieza cuando quieras. Me pasó igual. ¿Ya? Adelante.
So thank you very much for the introduction. This work is in collaboration with Denis Boyer, here present, Sandra Smith Aguilar, and Gabriel Ramos Fernandez at the National University of Mexico. This work was also published this year in the Journal of Physics Complexity. And the main objective of this work was to contribute to the understanding of the social structure of social systems. I mean, for a long time, social structure has been conceptualized as a collection of different types of interactions and relationships. In recent years, with the development of network science, social structure has been conceptualized and modeled as multiplex networks. This is the work of Sandra Smith Aguilar in this paper from 2019, in which they used 2-year interaction data of 23 free-ranging spider monkeys living in freely in Yucatan, Mexico. Using the data, they constructed this empirical weighted multiplex, in which in this visualization, the triangles are the males, the circles are the females, the same number of nodes in each layer. The lines are the interactions, and there are 6 different layers. Over interactions, namely embrace, grooming, and aggression, and space-based interactions, namely contact, proximity, and association. In this case, contact is short-range interaction, and association is long-range interaction. So the goal in this work was to propose a mechanistic model of network formation that could be able to reproduce the empirical characteristics of the weighted multiplex. However, there are certain considerations to be made before proposing a model. Spider monkeys have a complex social structure. According to the general socioecological theory of primates, social systems have 3 main components: social organization, social structure, and mating system. In the case of spider monkeys, there are 2 main empirical observations to be made. The first one is that spider monkeys live in communities with a high degree of fission-function dynamics. These dynamics have an effect on the network of relationships and thus the social structure. The second one, which is most important, is that they live in communities that vary in size, sex composition, with more females than males, and remarkably highly sex segregated, where the females are the less social sex. That means that they are the majority, but with quick interactions. Given these complexities, we, instead of considering the whole multiplex, we focus on the association network under a monoplex approach, because the weighted association encodes much of the information on the number of interactions, the time-based quality of interactions via an association index, and the expected empirical sex-based asymmetries. In this, in this visualizations, the triangles are the 7 males, the circles are the 16 females, and these 2 groups lead to 3 different types of connections: female-female, female-male, and male-male interactions. And in this plot, the average weight, you can see that while males are the minority group, they have stronger interactions than females. In this visualization also, we present some empirical values for these metrics: the average degree, the average strength, the clustering coefficient, the weighted clustering coefficient, the number of modules, and the weighted number of modules. The lines here represent the interactions. The width are proportional to these weights, which are the fraction of time 2 individuals are seen together within the same subgroup. As such, we consider a weighted social network with social network model with explicit homophily. The original weighted social network model was introduced by Kumpula in these physical review letters from 2007, in which the network evolution is governed by 2 mechanisms of type formation. The first mechanism is the global attachment, which encodes the information of serendipity interactions, and that lead to focal closure or random connections. These connections are controlled by the parameter P sub r that goes from 0 to 1. And the second mechanism is the local attachment, which encodes the information of interactions via friends of friends. This is cyclic closure or triadic connections, which are controlled by the parameter P sub t that goes from 0 to 1, plus a reinforcement mechanism, which increases the weight of the connections that participate in these triadic connections. On top of these mechanisms, we introduce a parameter Q, which controls the probability of homophilic male-female connections, which in the case of Q equals to 1 leads to fully mixed networks, and Q equals to 0 leads to fully segregated networks. We performed numerical simulations in the parameter space by varying these three parameters. And we found that our model recovers several empirical weighted metrics simultaneously with the statistical significance, namely the strength, the weighted clustering, the weighted number of modules, the average weight per interaction type, the weight distribution function. And in this example, I'm using this specific set of parameters. However, if we look at the distribution of fitted parameters, we found that our model works very well even for different age groups. And most importantly, we found that homophily is essential to recover the social structure. This is observed in the distribution of the parameter Q, which is strictly less than 1. Okay, there is a final validation to be made for our model. And here we need to go back to the socio-ecological theory of spider monkeys to test the strength of minority ties, something that is captured by our model. But there is this question: could this strength of minority ties be a consequence of this specific group composition asymmetry, homophilic effects, or network size? Well, we performed numerical explorations with the fitted model, considering this bipartition model with homophily, in which the males now are the minority group, the females the majority group. And we introduce another parameter, phi sub m, which controls the fraction of m-type nodes, and we vary the network size. And we found that by looking at the normalized average weight per each type, indeed, the strength of minority ties is a consequence of group composition asymmetry, homophilic effects, but is independent of the network size. This is not a trivial result, because if we change the fraction of the minority, but we have no homophily, we don't see the asymmetry in the weights. Also, if we change the segregation of the homophily, but we fix the fraction 50-50, we do not see this asymmetry in the weights of males and females. It is only when we change the minority and the homophily that we see this new phenomenon, a phenomenon that we consider is a fundamental network phenomenon, which is different from the strength of weak ties proposed by Granovetter in the 70s. So thank you very much for your attention.
Thank you for your talk and for being on time perfectly. We have time for questions. Are there any questions? I have a question. Can this same kind of model be extended to other social species and humans in particular?
Well, we could try it. I'm not presenting here the results, but we have applied our model to the full multiplex, and we have been able to reproduce all the 6 layers of interactions. Another, we tested with another data set of 20 years of association of these spider monkeys, and we have also reproduced the social structure with statistical significance. So the model is quite good to reproduce the social networks.
Okay. Any other question? So we thank José for his talk, and it's time for coffee. Gracias. Tenemos una pregunta en línea. ¿Puedes abrir el micrófono y hacer la pregunta, por favor?
Thanks. Can you hear me?
Sí, te oímos. Yes, we hear you.
Do you observe this structure based on weak and strong social ties that Granovetter describes in this paper in this society of monkeys?
Can you repeat the question, please?
Yes. Do you observe the social structure based on strong and weak social ties in this particular society of monkeys that Granovetter describes for human societies?
Well, we haven't observed that structure in the empirical data because, I mean, formally and rigorously, I mean, we have the empirical networks. I want to go back. If well, we cannot see it here, but the computational model, yes, it is able to reproduce those Granovetterian structures. Here. And yes, I mean, qualitatively, you can observe those communities, for example, in the case of embrace interactions. In the case of embrace interactions, again, the triangles are the males, the circles are the females, the lines are the connections, and the colors represent the communities. So in this case, or communities or modules. So in this case, the males are in one community, the females belong to another community, and because they are tightly tied together, and there is these weak links among these communities. But this is just a simple observation in the data.
Thanks.
So if there's still no questions, then it's a coffee break, and we reconvene here at 4 o'clock. Thank you, Jose.
Okay, hello everyone. We are starting 10 minutes later, but we have a quick announcement about the conference dinner.
Let's get started. Welcome to the final session of the day. Our first talk is an online talk. So we have our speaker is Oscar Fontanelli Espinosa. Oscar, can you hear us?
Yes, can you hear me?
Yes. So could you please share your screen?
I am doing this. Can you see it? Can you see it?
Yes. So full screen, correct? Okay, so please go ahead, Oscar. You have 15 minutes, including questions.
Okay, thank you very much. I work at a school for social science, so I wanted to show you a very direct application of a network science methodology in a particular problem in geography, and how even these simple methods can yield what we believe are useful and interesting results for social sciences. I'm talking about the problem of delineating uh, functional areas or regions in a given territory. This problem arises from a well-known fact in human geography in which people do not confine their activities within artificial boundaries of administrative regions. Instead, people everywhere, they travel and they commute every day from between different municipalities, different states, and even different countries in some societies. And this means that sometimes administrative units, such as municipalities or states, are not the best observational units when trying to do different studies of different kinds. So arises the need of defining new observational units, which are called in geography functional regions, that are regions or areas that divide that partition the territory and that pretend to capture the complex dynamics in which people actually inhabitate a given territory in a more organic way. There are different kinds of functional regions, economic functional regions, local market areas. Today I am focusing on functional areas based on human mobility. People have tried to delineate this kind of areas, specifically for mobility, in the last 10 or 15 years with different approaches. There is always a certain degree of subjectivity when trying to do this. So we propose here a purely data-driven approach to delineate the mobility functional areas of, of Mexico that, as far as we know, this has not been done yet. If we are able to delineate these areas, then we can ask questions about them, about their social-demographic or cultural or political characteristics. As I will show in a few moments, the data set that we utilized allowed us also to ask questions about how these areas changed and evolved at the beginning of the COVID-19 pandemic in Mexico. The approach that we utilize starts with origin destination networks. An origin destination is a network in which vertices represent areas of a territory or points of interest, in our case, municipalities in Mexico, and edges that are weighted and directed. They show flows of people from one municipality to another over a certain period of time, in our case, over different days. We we published last year a set of daily intermunicipal origin destination networks for Mexico for the year 2020. The data is, these networks were constructed from a very large database of mobile phone geolocation, and they are available for any of you that has interest in this kind of topics. They have this These formats, they are in edge list, and we provided there in that work information about how many mobile phones from our sample moved from one municipality to another on a given date, and this can be used to construct these origin-destination networks. Now, the idea of the approach is that mobility functional areas corresponds to the concept of community in a network. Recall that a community in a network is a group of vertices that has more internal connections between them in that group than to other nodes outside that particular group. And a mobility functional area, I am utilizing a definition that was given very recently in 2021 by this group of people working at the European Commission. A functional area for human mobility is, in our case, a region of municipalities that is more connected between them in terms of human flows than to other areas of Mexico. Communities in a network have high cohesion, which corresponds to the idea that mobility functional areas are internally coherent in terms of human mobility. Communities in the network have a high separation, and that corresponds to the idea that mobility functional areas are externally self-contained. So with this idea, and given that we have this set of 366 mobility or origin destination networks for Mexico, the approach is actually very simple. We utilize different community detection methods that are well known in network theory on these networks, and the communities that these algorithms will give us should be or should correspond to these mobility functional areas. There is a large degree of variation from one day to another in terms of mobility patterns. Mondays are typically different from Fridays, and weekends are different from weekdays. So we average out this variation by dividing our study period, which is the year 2020, in 3 different periods or stages based on 2 key dates on the development of the pandemic here in Mexico, what we call the pre-pandemic stage, the first stage of the pandemic, and the second stage of the pandemic. On each of these 3 time periods, we merge all the daily networks to end up with only 1 network for each period. So finally, we have 3 networks. And on each network, we utilize 2 different community detection methods, Luban and Infomap. Luban, that will give us a few large communities to observe mobility at a large scale, and Infomap allows us to observe mobility at a medium scale. These are the first results from the Luban method for the pre-pandemic stage, what we will call the base state. Then the pandemic started and lockdown started, and things began to evolve from this so-called base state. There are many things to observe and to comment here. First of all, that these mobility areas are actually geographically coherent and connected with very few exceptions. We also see, for example, that in some regions of the country, particularly in the north and in the southeast, the boundaries of mobility areas do coincide with political borders of states, which is normally not observed in other studies with other methodologies in other countries. But on other regions of Mexico, particularly here in central Mexico and on the southern coast, mobility areas do not correspond, or their boundaries are not given by political borders of states. To each of these communities or mobility areas, we compute very simple community metrics from networks, particularly the size, the number of municipalities that they encompass, the density, which is a measure of internal coherence of these areas, and the Krag-Hart index. Maybe that is not so common, but it is very simple. It is a measure of how disconnected a community is from the rest of the network. In this case, how is connected an area is from the rest of the country. And then a pandemic started and lockdowns started, and these patterns began to evolve in this way from up to bottom. I am coloring the communities by density, by the crack heart index, and by the rate of daily new cases. There are also many things to observe. For example, that there is this mobility region in the southeast of the country that is very stable through time. It is always there. It is well defined by state boundaries, particularly between Chiapas and Tabasco, and it is always very disconnected to the rest of the country. We also see, for example, that this one here, Zacatecas, is almost its own community, its own mobility area, and that is also very stable. Or, for example, the emergence of a region here in central Oaxaca, in red in the bottom right map, that was not present at the beginning of the pandemic or on the pre-pandemic stage. With the other method, the info map, we get around 80 or 90 groups. We are not trying to characterize each of them. There are too many. But we can utilize this large number of groups to explore possible associations between social demographic features of these communities and network features. For example, I show here that when a community is very large in terms of territory and has a large population, it tends to be very disconnected from the rest, so it is self-contained, but it is not as internally coherent as smaller communities, for example. We can also measure similarity between different partitions to ask when, if or when we have again the same mobility patterns that we observed before the pandemic, or to observe, for example, that the largest impact on these mobility patterns given by the lockdowns occurred during the first stage of the pandemic. So indeed, this methodology produces mobility areas that are geographically coherent. Zacatecas and the northern states, and also the region of the peninsula of Yucatan, are very stable. And we also observe that in those areas of the country where areas are well delineated by political borders, tends to be more stable and more disconnected from the rest than, for example, in central Mexico, where these political borders do not confine mobility flows. I would like to thank the collaborators, Professor Ricardo Mancilla, who I believe is here in the audience, and Leonardo Alvarado, a student at Facultad de Ciencias UNAM. Thank you for your attention.
Thank you for your talk. We have time for a few questions. Soham?
Hi. For this mobility, do you think that this mobility could be one of the reasons for spreading the infection from one place to another? I mean that if I calculate if I have been calculate how the what is the correlation between the spreading of the disease from one state to another, do you think it will be correlated with this mobility network also?
We believe it should, and we also, we have not done this that I'm going to say, but we can also measure flows from one community to another and maybe trace if that coincides with how the virus spread through the country.
Because different states have different measures at that time, right?
Yes, and that is also something that we observed here. I did not present those maps, but when the epidemiological stoplight system started at June 1st, different states had different lockdown measures, and we do observe that communities are better delineated by state boundaries.
Okay, thank you.
Yeah.
If not, let's thank Oscar again.
Thanks.
So our next talk is given by Manan Vyas. So please come.
Y ese es el control. Para adelante, para atrás y puntero. ¿Sí? Si quieres probarlo. A ver, todavía no me da aquí. A ver, ahora sí.
Sí, puntito.
Ujú.
Muy bien.
Ujú.
Good afternoon, everyone. First of all, I thank the organizers for this opportunity. I'll be talking about stock market data analysis using distance correlation coefficient. So the motivation behind this work was to look for nonlinear correlations in stock market data. So what is a time series? Okay, so what I show here is the closing prices of the SP 500 index, which is Standards & Poor's 500 index, from the year 2007 to 2023 for all the trading days. Okay, so this is the closing price for different trading days as I go from year 2007 to 2023, and this is a time series. Okay, so what features you see here is there is a trend. Okay, that the prices are increasing with time. All right, and then there are fluctuations. All right. Whenever we are doing the multivariate analysis, we look for stationarity in the time series, okay, to avoid the artifacts, okay. And a time series is said to be stationary if it satisfies that the mean, variance, covariance, and the correlation, which are defined over here, they remain stationary for all the times, okay. They are constant for all the times. I'm sorry. So in this picture, you can see this is a stationary time series, whereas these three, they are non-stationary as the variance increases in time, the mean is decreasing in time, and both the mean and the variance are changing in time here for these time series, okay? So the first thing we have to do is we have to convert our non-stationary time series into stationary time series, and that we do by computing normal returns, which is the difference between the prices at time t with the previous trading day price normalized by the price at the previous trading day, okay? And the previous time series that I showed now looks like this when I plot it in terms of the returns, okay? And as you can see, I still have these bigger fluctuations, okay? So only the mean is constant with time, okay? And that's why we refer to these as weekly stationary time series, okay? And that's what we deal with because we cannot get rid of these fluctuations which appear during the crisis periods. Okay, so the main input that goes into analysis is the data matrix, which is a rectangular matrix, non-symmetric. So there are n number of observables, and t is the total number of time period, which we call as time horizon, for which we have different time series. So this is data matrix. The first row you see is the time series for the variable x1. The second row is for the variable x2, similarly for x3 up to xn. Okay. And we can compute the covariances between pairwise variables and the variances for each of the variables. Using these two, we can calculate the Pearson correlation coefficient between the two variables xi and xj as the ratio between the covariance normalized by the variances. Okay, and the Pearson correlation takes values between -1 and 1. Okay, so when Pearson correlation is -1, we say the variables are anti-correlated. If one is increasing, the other one is decreasing, and vice versa. And when it is positive, they are highly correlated, that is, both will be increasing or decreasing. And when it is 0, the variables are uncorrelated, okay, but not independent, okay. It only shows that there are no linear correlations between the two variables, okay. So what we do is we want to look at a measure which might capture the nonlinear correlations that is there in the data. And that's why we start using the distance correlation coefficient. So what we do is between the two pair of variables, we calculate the pairwise distances and we center them. Okay, it's double centering actually. So what we are doing is we are changing the distances into scalar products by putting the center at the geometric mean. Okay, and then we can define using these double centered matrices capital A and capital B, distance covariance and distance variance, and calculate the distance correlation coefficient. By definition, it always takes positive values between 0 and 1. But when distance correlation coefficient is 0, the variables are independent. Okay, So there are no correlations whatsoever present between the variables. And this is the general structure of a correlation matrix. So what we have is we have ones on the diagonals, which are the self-correlations, and then we have the pairwise correlation coefficients between all the variables. It's a symmetric matrix. It's n times n dimensional, where n is the number of variables. Okay. When we have the time period is much, much smaller than the number of variables, this matrix will be singular, and it will have exactly n minus t0 eigenvalues, or n minus t plus 1, okay, depending on the normalization that we use, all right? Okay, so the data that I'm using for this analysis is the daily closing prices of 370 stocks, which are under Standards & Poor's 500 from the period August 2000 to August 2022, which is downloaded from Yahoo Finance. So we have in total more than 5,500 closing prices. We convert them into returns, which is 1 minus, okay? So we choose only the stocks which have been traded continuously during this time period, okay? And there are no 2 missed periods, okay? And this table gives the different sectors in which all the stocks are divided, okay? So all these 370 stocks, 11 are from communication services, 38 are from consumer dictionary, and so on. So what we do is, first of all, for the total time horizon, we plot the correlation matrices. This is the Pearson correlation matrix, and this is the distance correlation matrix. Now, because we are doing averaging over very long time periods, okay, we don't see any details here, okay? The only difference you will see is that the sectorial correlations are more prominent when we use the Pearson correlation coefficient in comparison to the distance correlation coefficient, okay? Now, we are plotting them from 0 to 1 because the minimum values for both Pearson and distance correlation are positive. Again, it's because of the long time averaging that the Pearson correlation doesn't take any negative values. So as I said, the disadvantage of working with long financial time series is the loss of information for short periods of time. So we divide the correlation, we divide the data matrix into short time series, which are epochs, okay? And the computing of returns and the treatment of epochs guarantees weekly stationary time series for that time period, okay? And these are the crisis and the bubble periods that I will be considering, okay? So now what we do is for each epoch, we construct the correlation matrix, and now we can plot the distribution of correlation matrix elements as a function of time, okay? So what you see for the Pearson correlation coefficient, you can see these peaks which are shifted towards the higher correlations, they belong to the crisis period, okay? I would like to point out the COVID crash here, okay? And the same thing you also see for distance correlation coefficient, okay? But they are all shifted towards the lower values of the distance correlation, the average distance correlation, okay? And these are the two-dimensional projections of the same plots, okay? And here you can see the crisis periods of 2011, 2015, and 19, okay? Those are the ones I would like to point out. And here, the same thing you will see, all right? In case of the Pearson correlation matrix, you will see that there are very few negative correlation matrix elements that you obtain in comparison to the positive ones. Okay. Next, we look at the distribution of eigenvalues, the time evolution again. So what you see here is each strip in this is the distribution of eigenvalues. And this red strip that you see throughout is because these matrices are very singular. Okay, you have 370 stocks, and I'm considering only 40 time periods, so I have only 40 non-zero eigenvalues. So I get a eigenvalue peak at 0, which is delta peak at 0, and then I have a bulk distribution, okay, which is like Marchenko-Pastur, but with correlations, and all these points that you see, they are the outliers, okay? Now, the largest eigenvalue represents the market states, and you will observe that during the crisis periods, the market states are very far apart from the bulk distribution, okay? And I would like to point out that these market states are linearly correlated with the average correlation, okay? The same thing we observe with the distance correlation as well, okay? We also look at the time evolution of the distribution of participation ratios. So participation ratios, they actually give the contribution, the number of components that contribute significantly to each eigenvector, okay? And again, we look at the time evolution corresponding to the Pearson correlation and the distance correlation. And this horizontal line that you see here, it corresponds to n over 3, which is the average value of participation ratios from Gaussian orthogonal ensembles, okay? So in case of Pearson correlation coefficients, we see a slightly upward shift during the crisis periods, Whereas in distance correlation, we see a slightly downward shift, okay? But for the Pearson correlations, always the distribution is well above the GOE mark, okay? Whereas in case of the distance correlation coefficient, it's pretty much around the GOE mark, okay? We also looked at the movements of these correlation matrices, how they behave. So this is the scatter plots between the mean and the standard deviation, skewness and standard deviation, kurtosis and standard deviation, the maximum eigenvalue with standard deviation, the participation ratio corresponding to the maximum eigenvalue as a function of the standard deviation, and the participation ratio corresponding to the maximum eigenvalue as a function of the maximum eigenvalue. The solid circles that you see, they denote the crisis and the bubble periods that we have, okay? In case of Pearson correlation, what we observe is that the gamma 2 is negative for the bubble periods, okay, but it is positive for the crisis periods. So it kind of distinguishes the bubble periods from the crisis periods. And in case of distance correlation, what we see is that the skewness is negative for the crisis periods, whereas it is positive for the bubble periods, okay? So in case of distance correlation, the skewness that distinguishes the bubble periods from the crisis periods. Next, what we do is we cluster these matrices. So what we do is we consider epochs of 40 days, which are non-overlapping. So we end up with 138 correlation matrices. So now we want to cluster them and see how similar or dissimilar they are, and whether we can have different features based on the Pearson or the distance correlation or not. Okay, so this is the distance matrix or the similarity matrix, which depends on the Euclidean norms between the distances in the correlation matrices at different times. Okay, so this left figure is corresponding to the Pearson correlation, the right one is corresponding to the distance correlation, and these thick stripes that you see, they all correspond to the crisis periods. Okay. So the structure is pretty similar, both for distance correlations and the Pearson correlations. These are the dendrograms. So in hierarchical clustering, what we do is we consider each of the correlation matrix as a singleton set, okay? And then we start combining them together until we reach a single cluster by minimizing the variance, okay? So this is corresponding to the distance correlation. We choose 5 clusters, both for Pearson and the distance correlations, and this is the state evolution of the market depending on the Pearson correlation, and corresponding to each state, these are the average correlation matrices, okay? And a similar figure for the distance correlations, okay? And these are the corresponding transition matrices that we have. And I would like to point out that even though when the Pearson correlation coefficient is very small, okay, the distance correlation is pretty high, indicating that there are higher order correlations that are present in this data. However, it cannot indicate the order of these higher order correlations, okay? And it's probably because the dynamics is governed by the maximum eigenvalue, and if we remove the maximum eigenvalue effect and then use these measures, we might be able to find something that differentiates the nonlinear correlations from the linear correlations in the data, okay? I'd like to stop. Thank you for your attention.
Thank you, madam. There is time for a short question. Any question? On the basis of these results, do you have any specific suggestions that what people should use, the Pearson correlation or the distance correlation?
It doesn't matter, okay? Because so far, everything is governed by the maximum eigenvalue, okay? So unless we remove the effect of the maximum eigenvalue, it is very difficult to say whether the distance correlation coefficient has any benefits over the Pearson correlation coefficient or not, okay? We also use the Spearman rank correlations, but it also points out about the linear or the monotonic relationships between the variables, okay? So there also, we didn't find any difference, okay?
And the second question is that in your correlation matrix, we have seen that there is dominant correlation in the sectors, and there are non-so-dominant correlations between the sectors. The question is that how do you define the sectors, or do you previously know about the sectors? And if you do not know about the sectors, is there any way that from the data you can define the sectors?
Actually, it comes from the data, okay? Because all the companies that are listed under the index, they are divided into these sectors.
So it's previously known?
Yes.
Okay. Okay, thank you again, Manan. There is a, okay, very short question, please.
Your last graph, you can see that in the cases where the Pearson coefficient takes small values, distance correlation is about 0.4.
Yes.
Might it be so that the distance correlation is more affected by random correlations, and that might be this increase? Is to say, if you're correcting with surrogate data, this effect disappears, or what do you think about that?
No, it doesn't go away.
Even if you're correcting with surrogate data, or is that surrogate corrected?
It's already clean data that we use here.
What does it mean, clear data?
Clean data means that, okay, so when we download the data from Yahoo Finance, there are many gaps in the data. We get not a number, okay? And if this not a number, it appears while downloading for more than 2 consecutive trading days, we drop those time series out.
Okay, but nevertheless, you're estimating these values over finite time horizons, and that produces random correlations, right? Therefore, I'm talking about the correction with surrogate data in order to subtract this effect.
What do you mean by surrogate data?
Well, maybe we can discuss it later on.
Okay, sure.
Thank you.
Thank you.
So let's thank Manan again, and let's move to the next speaker. Sí, ya lo tengo. All right. Our next speaker is Kevin Peralta Martinez, and we will talk about hyperbolic random graph scaling study.
Y para lanzar ese testimonio, retroceder esto y apuntas con esto. Ahí, perfecto. Gracias.
So, hello, thank you very much for having me here. So, in this work, I show you the hyperbolic random graph. And we, in this work, in collaboration with Dr. José Antonio Méndez Bermúdez, he's out the audience, we perform a scaling study of some spectral properties using random matrix theory. So, I don't want to state the obvious, but because many people have talked about networks, but in this case, we are interested in analyzing spatial networks. So, as an example here, I show you a graph or a network of the adjacencies of the lower 48 United States. So, of course, this network is embedded in a geometry. Okay, so that's why we call it spatial. On the other hand, and that's the reason why spatial networks seem to be very important, is that they're actually, we can find in real world networks that are embedded in a geographical territory. So here we have the network of natural gas pipelines in Europe, where the nodes could be interpreted as the intersections between pipes or gas stations. So in general, we can say that one is interested in analyzing networks and real networks because we could be interested in how different cities around the globe connect. That's maybe transportation, how people interact with other people from other cities, and so on. In particular, it's very interesting that spatial networks can be related to networks that are actually not embedded in a geometric space. So that is a case of the World Wide Web, which connects devices and sends information, so we know it, we use it every day. And it's proved that, in particular, the hyperbolic random graph models pretty well this real network. So how we study networks, some presentations ago, someone explained the adjacency matrix. So just to review it, for example, here we have a graph with nodes A, B, C, D. And say, for example, node A is connected to node B, node D. So the entries AB and AD in the adjacency matrix become a number 1. Okay. So notice in particular that this matrix is symmetric because we have a non-directed version of the graph. So a very interesting thing here is that, that we can define the degree of a node. The degree is basically the number of edges a node has. So for example, node A, we count it's connected to B and to D, so the degree of node A is 2. And it can also be related easily to the adjacency matrix by this equation over here. So the hyperbolic geometry. This model was inspired, I think, this model was inspired on a random geometric graph, which is embedded in a Euclidean space. So this is a generalization in the hyperbolic, in 2-dimensional hyperbolic space. In particular, we use the Poincare disk, which has different traits. One of them is that the geodesics are circular, orthogonal, are circles orthogonal to the unit circle, as we can see here in this figure. And the unit circle boundary shows points that are infinite, stay at the infinite radius position. So just to show why this is exactly hyperbolic geometry, we can see that a triangle here, lines L1, L2, and L3 form a triangle where the summation of the angles is less than pi. So, and in this figure here, just to clarify, this is a tessellation. So there are triangles and heptagons embedded there with the same size. And we can see that as we go further from the center of the disk, the figures seem to be smaller to the eye. So the model was introduced in 2010 by Kirkup and others, and this basically distributes n nodes in a Poincare disk, and in this case the positions are assigned from radial coordinates drawn from this density function over here, where alpha is the uniformity parameter, rho is the size or the radius of the disk, and some angular coordinates from a uniform density, which are connected, the nodes are connected according to this Heaviside function, which relates the size or the radius of the disk and the distance between nodes that satisfies the hyperbolic law of cosines, where the hyperbolic law of cosines is defined by this parameter zeta, that is the parameter that relates the curvature of the embedding space. So one interesting trait here is that we can see a power law degree behavior in general for this model, which is characterized by the beta parameter here. And at the same time, this beta parameter is given in terms of the ratio alpha over zeta. So alpha states how uniform distributed, how the nodes are distributed throughout the disk, and zeta says what's the curvature of the space. So here we can localize 3 regimes: one that's above 1/2 value, one at 1/2 value, and another below. So here's an example, just to show you how it may look like a hyperbolic graph. On the other hand, and as I told you, here there's an histogram of the degree distribution of the internet, which shows a power law behavior. That's why it's can be related to the hyperbolic random graph. So we analyze spectral properties by defining a weighted adjacency matrix. So you can see that the connection is straightforward because we substitute the non-zero entries of the adjacency matrix by random numbers from a normal distribution with mean 0 and variance 1. So notice that we fill the main diagonal also. So we perform numerical diagonalization, and we can see transition from a Poisson ensemble to deleted ensembles, and then to full GOE as the adjacency matrix becomes fuller and fuller. So what spectral properties can we measure? One of them is given the adjacency matrix that is orthogonal, we can get real and ordered spectra of the adjacency matrix. So we can define the ratio between consecutive level spacings for different curvatures and different sizes. Here, the blue curve corresponds to 250 nodes, the red one to 500, and the black one to 1000 nodes. So different curvatures here are represented by symbols. I hope you can see them. And we can see that by fixing the radius of the different regimes of the power law behavior, if we plot this quantity as a function of rho, we can see that as the curvature increases, the chords are displaced to the left. Also, we can see the whole transition from the GOE limit value towards the Poissonian value. Additionally, we can see that by plotting the same quantity as a function of the average degree, we can observe that these chords may have a scaling parameter. So we can also compute the Shannon entropy, which is takes into account the normalized eigenvectors of the diagonalization. So it's basically the same. We plot the Shannon entropy as a function of rho at 3 different radius and for 5 different curvatures. So again, we can see how these curves change as the ensemble regimes are explored as the rho parameter grows. Additionally, we can see the average degree. How, again, a very important thing here is that curves of the same size at this point and different curvatures fall one on top of the other, so they merge. So this tells us that we can find, of course, if we normalize the curves, we can see that they are alike. And this tells us that we can find easily a scaling parameter of these spectral properties. So how we do this? We basically find the value of k at the middle of the transition between regimes. So that's for normalized curves at 0.5. Here we find the values of k, and we define this parameter over here, that is a function of the size and the average degree. So basically here we have the same curves previously shown, but as a function of the scaling parameter. So here are the fitting values. As we can see, the best fitting belongs to the critical point of the regimes, that is 0.5 ratio. And well, time short. So some remarks and final comments is that we can employ random matrix theory to study different models of networks. In particular, this is a very interesting model of a lot of interest in network science. And well, we can characterize universal curves as a function of the size of the network and the average degree. And one important thing here is that, as you've seen, we have explored 3 values at the 3 different regimes of the heterogeneity of the model. So that's it. And here we have some references for the reading if you're interested in this.
Thank you for your talk. Are there any questions? Okay. There's a question.
I'm not quite clear. Why should there be a really sharp transition between these various degrees of heterogeneity?
Do you mean the ratios?
Yeah.
Yeah, well, it should happen because of the distribution, the power law distribution. So basically, we expect big changes for a rate when the ratio goes above that critical point. So that's basically the idea. So what does it mean? That nodes with, sorry, that more nodes will have few connections or few links. That's basically why that's critical point. Yes.
So we don't have time for more questions, so let's thank Kevin again. And the next talk is online. The speaker is Gabriel González Contreras. Gabriel, can you hear us?
Yes.
So could you please share your screen?
Mhm.
We cannot see anything.
Can you see my presentation?
No, we see the schedule of the meeting.
Okay. Can you see my presentation now?
Yes, we can see it. So, well, our speaker is Gabriel González Contreras. The title of his presentation is Diffusive Transport Through a Wedge-Shaped Narrow Channel Under Stochastic Resetting. So you have 15 minutes, including questions. Go ahead.
Thank you very much. Well, yeah, I'm going to talk about a recent project that I started like a few months ago. I'm not an expert on resetting, but I started work a few months ago. And the title of my presentation is Diffusive Transport Through a Double Cone Under Stochastic Resetting. So the outline of my presentation is the following. First, basically my talk is going to be divided into 3 parts. On the first part, I'm going to talk about the main concepts needed to understand diffusion of particles with resetting. Basically, I'm going to go through the concepts that Dr. Mahundar gave in his really nice talk yesterday. I'm going to talk about concepts such as Brownian dynamics, target search via Brownian motion, and resetting. And then on the second part of my talk, I'm gonna introduce diffusion of particles with through channels using the fixed Jacob equation and how one can introduce resetting into these equations. And at the end, I'm going to talk about the numerical simulations that I have done to validate the theoretical results. And at the end, I'm going to give the conclusions of this work. So Brownian motion was first discovered in 1827 by the Scottish botanist Robert Brown, which he saw under the microscope that tiny particles suspended within a fluid were moving in a random motion. And this was really surprising because from a Newtonian point of view, there were no external forces acting over these tiny particles. it was not until 75 years later that Einstein explained this Brownian motion by this equation, which is the diffusion equation. This is the diffusion constant, and Einstein assumed the existence of atoms, and these tiny particles move because these atoms were pushing these particles in a random way. So a few years later, Paul Langevin gave another description of the same phenomena. He used a Newtonian approach. He basically explained Brownian motion by assuming that particles were subject to two different forces. One was a random force and the other one was a drag force. And this is what, this was the first stochastic differential equation. And the two approaches were, they coincide through this diffusion constant and the drag coefficient through this nice formula. And now, well, let us consider, for example, one-dimensional walker that starts like a Brownian motion or diffusion, and we would like to know the time it takes to this walker to get into to a certain position, say, for example, L, that we can call the target, and we would like to know the time it takes this particle to reach this target. This is known in the literature as the first time passage problem. And if we would like to know the mean first passage problem, we will need to have a lot of walkers or a lot of different trajectories starting from this point, and we will need to measure the time it takes to each particle to reach this target function using the fixed Jacob formalism. And the answer is yes. If you use like a double cone, for example, like this, you will see since the diffusion function has the derivative of the radius is a square. It doesn't matter if you have a positive slope or a negative slope. So in this case, you still have a constant diffusion coefficient, and you can what I did is that I calculated the diffusion transport of particles through this double cone. What I got is this formula right here, and as you can see here is that if you have a linear relation of the radius, this term drops out, and you have like a normal diffusion. But in our case, since we have a double cone, this term, you have a kink right there. So this term, for the double cone, you will have a Dirac delta function. So basically what I did is that I calculated the mean first passage time for these particles going through this double cone geometry. And I got this really big expression for the mean first passage time without resetting. And that if you plot this for different values of the slope, for example, you will have for a cylinder, you will have like a upside down parabola. And for different slope, for slope different than zero, what you will get for the mean first passage time is like a double, like a heart-shaped plot. I did this for the case of particles without resetting. You have the heart-shaped plot, and with resetting. And basically what I get is pretty much the same conclusions that they got for the single cone. If you're really close to the boundaries, it's a good idea to have a resetting for the escape times of the particles. Otherwise, I mean, resetting is not that good. But this double shape, I mean, this, for example, you have a minima, no, here, which is a nice feature of having this double cone geometry. So then what I try to do is that I try to use finite element method software, which is known as CUCEI, to modulate this problem. So what I did first is that I tried to calculate the mean first passage time for the case of a cylinder by solving the Langevins equation by using this software. And what I got is pretty much the upside down parabola, which is good, which is what I was expecting. But the downside of using this commercial software is that I mean, this simulation took me 11 hours, no, to get this plot. So anyways, also if you plot the analytical result versus the numerical result, well, what you get is not what's it like a qualitative result of what would you expect from theory, which is not that bad, but I would like to get a closer numerical solution to the analytical solution. And also what I did is that I calculated with this software when you have the other plot, this one was for the cylinder, and for the double cone geometry I did the calculations with this software, and I got the heart-shaped plot, which was good. I'm still working on the numerical solutions with resetting. I'm pretty much also I have some preliminary results, but still I didn't want to show these results here on this presentation. But for the conclusions of this work is that well, what I showed here is that this fixed Jacob equation can be used also for a double cone geometry. You can get exact expressions for the mean first passage time, and it has this nice feature that you have also a minima right at the middle of the cone. And also, well, I have validated at least qualitatively the results by using this finite element method software, CUCEI multiphysics, which pretty much agrees with theoretical predictions. And for the future work, I'm gonna plan to add resetting into these numerical simulations. And this work was supported by a science project that I had. I would like to acknowledge CONACYT for this financial support, and this will be all for my presentation.
Thank you, Gabriel. There is time for some questions. Yeah, okay. Well, you raised your hand at the same time, so but well.
When you use CUMSOL, is this for solving the partial differential equation, the diffusion equation? Or why don't you use simply random trajectories?
Actually, yeah, you can use CUMSOL to solve either the diffusion equation or the Langevin equation. So what I solved here is the Langevin equation. The diffusion equation, I have solved the diffusion equation analytically. So what I tried to do was to use the Langevin approach, because I mean those are two different ways to approach the same problem. So I would expect to have the same solutions, either by using the diffusion equation or the Langevin equation. In this case, I used the Langevin equation because you can have these nice animations, simulations. So I try to simulate all the particles released from a certain point, and I calculated the mean first passage time, or the time that it takes to the particle to go outside the cylinder.
It's very strange that it is so slow.
In this cylinder?
No, that the simulation takes 11 hours.
Yes, because it uses a finite element method. I don't know if you.
But finite elements are for partial differential equations.
Sorry?
Finite element methods are for partial differential equations, not for trajectories.
Yeah, yeah, that's true. This is the downside of using like software. I mean, you don't know exactly what you're using. It's like a black box. Anyways, the console multiphysics software is advertised as a finite element method. I'm not pretty sure what it uses to solve the Langevin equation. But I mean, when you run the simulation, I mean, you get a mesh and everything. What it's done as using the finite element method, and I'm not certain if it uses it or not. But what I'm certain of is that it's solving the Langevin equation. That's all I can tell you.
Okay, thank you.
There is a second question over there.
And how can you explain that the mean first passage time, when you start just in the middle of the domain, can be smaller than when you start closer to one of the edge? Is it possible?
That's a good question, actually. That's a good question because, as you can see here, can you see my screen, right? You see my screen?
Yes.
Right here, yes, as you were saying, apparently a particle that starts right in the middle, it takes less time to get outside of this double cone geometry. I guess that if you start, for example, from let's say from the middle of the first cone, you start to maybe bouncing from the walls. I'm not pretty sure, but that's a nice picture that I found from this analytical theory. And I guess the physical reason is that if you start here, maybe you don't interact that much with this slope or with this other slope as you start from this side, let's say. But I'm not sure. I'm not 100% sure about that. But that's something that got my attention also.
Okay, thank you.
So thank you, Gabriel.
Thank you very much.
And our final talk of this session is online. So Oliver, can you hear us?
Yes, I can hear you.
All right, so the talk will be given by Oliver Lopez Corona. The title of the talk is Ecology of the Sacred as a Process of Intergenerational Antifragility. So you have 15 minutes, including questions. Please go ahead. Yeah, please share it.
I think I can't. Okay, are you seeing my presentation there?
Yeah.
Perfect.
All right.
So, thank you to the organizers for such an interesting event. I'm very happy to share with you a general framework that we have been developing in terms of intergenerational risk management. This is a work among other colleagues with Elvio Ramirez Carrillo, Pablo Padilla, Sergio Mendoza, Menoli Paul, Nelson Fernandez, and John Lovett. It is interesting because this is a very high multidisciplinary effort. Pablo is mathematician, Sergio is an astrophysicist, Nelson is a biologist, Elvia is ecologist, and John Lovett is a world-renowned ecologist. So it's a very interesting way to approach to an interdisciplinary question. So, think I can't. Okay. Maybe no. Okay. Okay. I was at the end. As you may know, we are facing a planetary environmental crisis, which has generally been characterized by climate change as the iconic representation of it. Despite the presence of multiple signals of its existence, take for example terrestrial biosphere degradation or ocean acidification. The change is so profound that there has been an extensive discussion about whether we are entering or not into a new geological era. Regardless of that, it is clear that we are in a peculiar epoch in ecological and evolutionary history of the Earth, characterized by the effects of human activities, and therefore it has been named Anthropocene. So, being in front of such a clear civilization threat, why have we been failing even on starting to respond? We understand the physics of climate change pretty much. We even model it with great detail. In fact, the Nobel Prize in Physics for 2021 was awarded partially on these topics. So, how is possible we cannot generate an adequate response to the problem? Well, because it is not a scientific problem. It is an intergenerational risk management one. Consider how all living systems, in order to survive, needs to acquire data, then after a computation, use the resulting information in an inferential process to generate new knowledge that finally is used for modeling environment and act. This chain of processes we call CIMA, C-I-M-A, for the letters of uh, computation, inference, modeling, and act. It is evident that if we have a population of living systems with different types of CIMA, eventually under ecoevolutionary processes, only the best CIMAs will be predominant. Interestingly enough, we know that when systems are in criticality, they achieve maximum computational and inferential capabilities, and it is then clear that CIMAs will follow a general arrow of criticality. But of course, living systems are not isolated, so the informational environment in which these ecoevolutionary processes occur is key. Now, the big question is, which is the best CIMA for different types of informational environments? Is it Occidental science? We think that it depends on the data characteristics and therefore on the informational nature of the environment. Consider simple versus complex environments, which may produce data that is either one, of low dimensionality, low uncertainty, objective, reproducible data, or two, high dimensionality, high uncertainty, subjective, non reproducible data. Our hypothesis is that for type 1 of data, the best CIMA possible is science and technology, but for type 2 data, the best CIMA acquires an heuristic form of philosophy, traditions, rituals, and the sacred. In terms of following ideas of Taleb, systems may classify in terms of how they respond to specific perturbations. Take, for example, this cup of glass. It does not like perturbation randomness of time. Um, it may respond usually in a nonlinear concave way to well-defined payoff functions, as in this scheme below the D. We have also systems that respond in a robust or resilient way that in which they are basically blind to perturbation. And there are also antifragile systems if they have a nonlinear convex response, meaning that they may even get better because of the perturbation. They change and adapt, of course, up to a point. We have been applying this antifragility framework to try to understand um, a more general features of complex systems. And in this paper that has been recently accepted for publication in Nature Complexity, we show that antifragility is the universal way in which healthy, or let's say complex systems in its best configuration responds to perturbation. Even more, Pineda, Kim, and Gershenson in 2018 has shown that one may use complexity as a universal payoff function. In that sense, we may be able to assess antifragility as changes in the system's complexity due to a perturbation. In that track of ideas, we have been applying antifragility to understand the health of ecosystems from the scale of terrestrial ecosystems such as a forest to the planetary ecosystem. These ideas are not quite new. There's a very well known work by Berkos that has built a very interesting field that he called sacred ecology, not ecology of the sacred, sacred ecology, as a complement to scientific ecology that explore the rich knowledge systems preserved by indigenous and rural communities worldwide, asking how modern society can benefit from these traditional ways of understanding the natural world. And on the other hand, using the anti-fragility framework of Taleb, he and his colleagues, especially Mark Spitznagel, has achieved a tremendous success making money with hedge funds as Universa. This was like a big news because of the pandemics. They made a lot of millions of dollars using among other strategies what in finance is called clipping the tail, that limits or eliminate extreme losses, also known as tail events. In that sense, we think that heuristics kind of CIMAs, as the secret, work via negativa. Via negativa means like provisions. What when not to fish some kind of fishes, not cutting down some areas of the forest, and so on. As a mechanism of clipping the tail of socioecological outcomes, especially those that may lead to population or civilization risk. So, in general terms, what I wanted to share with you is like this general idea we are developing, in which there are many parts that will need to hard work in terms of mathematical descriptions, such as what does sufficiently simple means, no? Maybe in terms of probability theorems, or maybe in terms of this kind of physical approaches by Frieden in terms of fisher information. And there's also, of course, much more practical avenues for this field in terms of applications in in natural resources management or production systems such as milpas or chinampas or this kind of projects. But in general terms, the idea of circular ecology aims to understand the nonlinear convex response of socioecosystems, which are in deep complexity in terms of intergenerational viability of their socioecosystemic functions in face of natural and social perturbations. This is achieved through an appropriate combination, and here we try to separate the three types of CIMAs. The logical CIMAs, science and technology, that of course would be the best for those informational environments that are simple enough. An intermediate kind of CIMAs that we call aesthetic CIMAs, like myths, art, direct contemplation of nature that enhance behavioral changes in people and the sacred, and practical CIMAs that in certain way function as reservoirs for ecological knowledge and allow it to keep them along long terms of times and enhance the transmission in intergenerational range of time, such as dances, traditions, and rituals that introduce tail tripping strategies to avoid catastrophic events. In that sense, our proposal differs from the Berkeley's ideas by introducing this CIMA concept that we think it's the key to mathematicize the problem, and also it allows us to understand the ecology of the ecology of the secrets in terms of when and how this kind of heuristic schemas emerge as the best framework for risk management. So in a kind of conceptual figure that considers the problem as a metaphoric lake of human civilization, intergenerational and anti-fragility, we think that this lake is nurtured from the rivers of different schemas that through eco-evolutionary processes achieve maximum anti-fragility for a specific informational environment. These different schemas manifest in different epistemological basins, for example, standard ecology, from simply enough informational environments, or in the case of deep complexity informational environments, indigenous science that has attracted a lot of attention. There's even a very nice comment in Science about how it is time to take indigenous science into the main discussion. Traditional ecological knowledge or sacred ecology a la Berkes. Our proposal of ecology of the sacred then not only offers a more general ontological basis, but also in terms of episteme. In this metaphor, we think that it could be seen as a kind of management system that couples and coordinates the flows of all tributary rivers that convey into lake. In this sense, we are trying to construct a kind of couple control systems in which one part of the control systems is a traditional SEMA, science and technology, and the other part of the control systems is this kind of heuristical approaches. With this coupling allow us to have different kinds of time scales and also kind of complementary balancing processes. And if you are aware of criticality ideas, this kind of balancing processes is one of the key features of criticality. So in some sense, our idea of the ecology of the secret is also trying to emulate criticality in these meta control systems for socio-ecosystems management. And for my part, that's what I wanted to share with you today. I think we are in time.
Thank you, Oliver. Are there any questions?
We are on time.
So how does this go along with evolution? Is evolution on longer time scales for you, or how would this be compatible with evolution?
Exactly. In this context, evolution is in a more long time scales. This is very interesting because, for example, Alejandro Frank has this idea about how in humans and many other animals we have two kinds of networks of response. For instance, we have a very slow network in our genome, and we have, and it is coupled with our more faster response network in our microbiome. So there are a lot of human kind of adaptations to very quick environmental changes.
Yeah, but it's all fine. But how is this mathematically or logically consistent? You know, because it has to be combined somehow. So evolution will be then influenced by basically that what you propose, what is also generically there, your sacred, whatever. Yeah.
Okay.
And so this would actually perturb or influence evolution in a way which is not included in evolution so far. And which should have given a different path of evolution, in my opinion. And a second argument is that there will be catastrophes, and we know about catastrophes where all these sacred things go lost in no time, basically.
Yes.
So, and this is kind of the overarching, how to say, processes which are included in evolution.
Correct. In the first part, we have been developing an ontological approach for evolutionary processes. We call that the ecobiome. In this new approach, we think that in general, our organism has a pool of genes, a pool of the genes of their symbiotes, and of course, that's the holobiont, the classical holobiont. But there are also cultural informational units that can be transmitted intergenerational, and all those pools combined work in an evolutionary process. So in this case, all this idea about ritual, the sacred, of any kind of cultural informational unit or ecological knowledge that can be transmitted from generation to generation, it's allocated in this kind of cultural group. And yes, of course, we are thinking in some kind of coevolutionary processes that include the holobiont and its cultural part. So this is kind of an extension of the holobiont ontology. Of course, you are right. Even the most antifragile systems are antifragile up to a point. No? There's always this kind of dosage response curves. And of course, if the perturbation goes beyond some threshold point, even if the system was antifragile before, it can stop to be antifragile and break. No? And we have a lot of examples of civilizatory collapses in that sense. No? Maybe a good example of that is the Pascua Island. No?
Okay, thank you. Any other question? If not, we thank Oliver again. And we close the session. So let's thank all the speakers today. Let's meet outside, just right outside for going to the dinner.